Just last night, a spacecraft carrying 4 astronauts ascended into the night sky, a vessel that one former NASA engineer insisted should never transport a human crew. The fundamental reason for this particularly dire warning is rooted in the performance of its heat shield, which had already shown signs of critical failure. During its last uncrewed test flight, more than 100 pieces of this protective material were torn away during the intense heat of atmospheric reentry. The shield returned with deep gouges and holes, damage that was considered so severe that NASA made the decision to conceal the photographic evidence from the public for more than a year. When an expert on heat shields, who had been instrumental in the first shuttle mission after the Columbia disaster, was finally shown the images, he made his concerns public. He explicitly informed reporters that his professional verdict was an unequivocal no, that human beings should absolutely not be flown on this particular machine. In his view, the agency was repeating the very same errors that led to the tragic loss of the Challenger and Columbia crews, where mission schedules took precedence over safety and computer simulations were trusted over real-world testing. All of this raises a deeply unsettling and unavoidable question. Has history begun to repeat itself? Despite these grave warnings, NASA made the decision to proceed with the mission. Last night at 6:35 inches the evening, the most powerful rocket ever entrusted with a human crew ignited its engines at Kennedy Space Center, generating a colossal 8.8 million pounds of thrust. Securely strapped inside the capsule at the rocket's apex were 4 people, sitting atop a heat shield that both its supporters and critics acknowledge will almost certainly crack again during its fiery return to Earth. The only remaining point of contention among experts is whether those anticipated cracks will prove to be catastrophic enough to cost them their lives. As we speak, those 4 astronauts are actively traveling farther from our home planet than any person has in more than half a century, on a trajectory toward the far side of the moon. During their journey, they will lose all communication with their home world and set a new record for the greatest distance a human has ever traveled from Earth. Following this, they will pivot back, hurtling toward our atmosphere at 25,000 miles per hour, facing 5,000-degree plasma, protected only by that same compromised heat shield. This, in its entirety, is the unfolding story of the Artemis II mission, and it is a story that is happening right now. Here on Calm Space, we would like to invite you to join us as we embark on these quiet explorations of the cosmos. Our community often finds that discussing the topics in the comments and engaging with one another's thoughts enriches the experience, as it is in the act of sharing our unique perspectives that the most rewarding and profound discoveries are often made. Tonight, the destination for our shared journey is a truly extraordinary one. We will follow 4 human beings as they embark on a mission aboard a machine that some experts believe is not safe for a crew, a machine with a known heat shield issue, propelled by 8.8 million pounds of force. This craft is destined to carry them farther from Earth than any person has ever gone before. Our journey will trace their path from the launch pad at Kennedy Space Center, through the hazardous radiation belts that encircle our planet, and out into the vast emptiness between the Earth and the Moon. We will be with them in spirit as they achieve orbit around the lunar far side, a point where they will be completely cut off from all contact with home before they begin their high-speed return. And we will remain with them through the final, critical 5 minutes of their voyage. These are the 5 critical minutes during which the temperature just outside their window is projected to soar to an incredible 5,000 degrees. The 5 minutes when the heat shield that has failed once before becomes the only thing separating them from annihilation. This is the story of Artemis II, what is arguably the single most perilous return journey in the entire history of human space exploration, and it is a journey that is taking place as we speak. Chapter 1. The Shield That Might Kill Them. It all began in December of 2022, when NASA conducted a crucial test flight, launching an uncrewed capsule named Orion on a journey around the Moon. This mission, designated Artemis I, was the maiden flight of the Space Launch System, the most powerful rocket ever constructed. The capsule successfully traveled to the Moon, completed a loop around it, and returned to Earth. In the public sphere, NASA hailed the mission as an unqualified triumph, with press releases celebrating its flawless performance as engineers celebrated their success. The agency then confidently moved ahead with its plans to place a human crew on the next flight. But concealed behind these celebratory public announcements, a deeply disturbing secret was being kept. The capsule's heat shield had come back from its journey severely broken. When the recovery teams and technicians at Kennedy Space Center retrieved the Orion capsule from its splashdown site in the Pacific Ocean and transported it to their processing facility, they were confronted with an unsettling discovery. The heat shield, the crucial curved barrier of ablative material designed to protect the capsule from the searing temperatures of re-entry, was riddled with extensive and unexpected damage. More than 100 different locations exhibited this alarming erosion. Significant chunks of the material had been ripped away, leaving deep scars across its surface. Furthermore, 4 separation bolts had partially melted through their protective thermal barriers. This specific type of damage was not what the sophisticated computer models had forecasted, nor was it consistent with what ground-based testing had indicated. What they were looking at was an entirely new and previously unforeseen mode of material failure. For more than a full year, NASA made the institutional choice not to make the official photographs of this extensive damage public. The first subtle indication of a problem emerged in March of 2023, when Orion's program manager, Howard Hugh, noted during a press call that there had been more variations across the heat shield than expected. He explained that the charred material had ablated in a manner different from what computer models had predicted. Crucially, he did not share the actual pictures, nor did he describe the deep gouges or make any mention of the partially melted bolts. The full scope of the problem only came to light in May of 2024, with the publication of a report from the NASA Office of Inspector General. The photographs that were finally included in this official report were nothing short of alarming. The released images revealed a heat shield that was visibly pockmarked with numerous holes and voids. Chunks of the ablative material, known as avcoat, some the size of bricks, had broken off during re-entry. This was simply not how the advanced material was engineered to behave. Avcoat was designed to char and flake away in a smooth, controlled manner, carrying intense heat away from the spacecraft. Instead, the evidence strongly suggested that gases had somehow become trapped within the avcoat blocks during the mission. As the capsule plunged into the atmosphere at 25,000 miles per hour and temperatures approached 5,000 degrees Fahrenheit, these trapped gases violently expanded. The resulting internal pressure buildup then caused the material to crack and be ejected in irregular pieces, leaving the heat shield scarred and its integrity compromised. In a deeply ironic and dangerous turn of events, the very material that was designed to protect the crew had, in a very real sense, turned against itself. The ultimate root of this critical problem can be traced all the way back to a fundamental design decision that was made many years earlier. The original heat shields for the Apollo missions utilized a single, continuous honeycomb matrix composed of roughly 320,000 individually filled hexagonal cells. It was an elegant and, most importantly, a proven design that had worked flawlessly on every mission. For Orion, however, NASA opted for a different method. Instead of a unified honeycomb structure, they bonded approximately 180 individual blocks of avcoat onto a carbon fiber skin. The critical fact is that no one had ever before flown a segmented heat shield of this particular type at the extreme velocities associated with a lunar return. Moreover, Orion is not a small vehicle. It is about twice as heavy as the Apollo command module. A significantly heavier spacecraft, by the laws of physics, re-enters the atmosphere with substantially greater force, resulting in more extreme temperatures and tighter margins for error. This deliberate departure from a proven, flight-tested design introduces a significant and potentially dangerous variable into an already high-stakes equation. And it is precisely at this point where the story takes a profoundly uncomfortable turn. After discovering this critical damage, NASA did not opt to replace the heat shield for the next mission. They did not choose to construct a new one from scratch, nor did they even decide to conduct another uncrewed test flight in order to verify a potential fix. Instead, their proposed solution was to alter the capsule's re-entry trajectory. On the Artemis I mission, the capsule had performed what is known as a skip re-entry. It first dipped into the upper layers of the atmosphere, effectively bounced off of it much like a stone skipping on water, and then plunged back in for its final, fiery descent. This decision ultimately raises a profound and pressing question about the agency's approach to risk management. Is merely changing the flight plan ever a truly sufficient fix for what appears to be a fundamental flaw in the hardware itself? The initial flight plan for the mission had involved a complex skip profile, a specific technique that would have created cycles of intense heating and subsequent cooling, which in turn allowed dangerous gases to build up inside the avcoat heat shield material. To address this fundamental problem, NASA's engineers pivoted to a direct re-entry. In this completely new scenario, the capsule would plunge straight down into the atmosphere in one single continuous burn. There would be no skip, no intermittent cooling cycle, and therefore no opportunity for those internal gases to accumulate and dangerously expand. But this proposed solution presented a very significant trade-off. A direct re-entry would subject the crew to much higher G-forces, and the vehicle itself to a steeper angle of attack and a more intense, highly concentrated burst of heat. NASA officially argued this approach would eliminate the specific conditions that led to the catastrophic cracking seen on Artemis I. The heat shield would still develop cracks, a fact that was widely and openly acknowledged. The core belief within the agency, however, was that these cracks would be manageable and ultimately survivable for the crew. This critical conclusion, however, was not universally accepted within the aerospace community. The most prominent and credentialed voice of dissent belonged to a man with an almost unparalleled understanding of heat shields, Dr. Charles Kamada, a former NASA astronaut who also holds a doctorate in engineering. His entire career is deeply intertwined with the subject of thermal protection. He once served as the Director of Engineering at Johnson Space Center, and in 2005 flew aboard the Space Shuttle Discovery. That particular flight was the very first crewed mission after the 2003 Columbia disaster, a national tragedy caused by critical damage to the shuttle's thermal protection system, which claimed the lives of all 7 astronauts. It was precisely this type of catastrophic failure that Kamada had dedicated his professional life to studying and preventing. When he personally examined the photographs of the damaged Artemis I heat shield, he was deeply alarmed by what he saw. His concern then intensified when he learned NASA was planning to fly a crew with the same fundamental design, but without conducting a prior unmanned validation test of the new, more aggressive re-entry profile. It was at that point that he decided he had a professional obligation to go public with his concerns. In a subsequent interview with CNN, when asked directly if he believed Artemis II was safe to fly, his answer was a stark and unequivocal no. He described the performance of the heat shield as deviant and went on to assert that NASA had constructed what he termed toy models, specifically to retroactively justify its decision to proceed with a crewed launch. He argued that the very computational tools now being used to analyze the problem were the exact same ones that had failed to predict the issue in the first place, a deeply troubling paradox. This raises a critical question about the faith being placed in simulation when available real-world data suggests a completely different story. Then, Kamada delivered a statement that sent a palpable chill through the entire aerospace community. He drew a direct and damning parallel between the current situation and the institutional behaviors that preceded both the Challenger disaster in 1986 and the Columbia disaster in 2003. The specific patterns he identified were hauntingly familiar to students of NASA history. He saw intense schedule pressure beginning to override the long-established culture of safety. He witnessed dissenting engineering voices being systematically dismissed or marginalized within the program, and he observed a dangerous reliance on computer models as a substitute for necessary empirical testing. It was, in his expert view, the same motivated reasoning and the same powerful institutional momentum, all pushing inexorably toward a launch date that had already been delayed too many times. Another former NASA astronaut, Danny Olivas, who had served on an independent review team for the agency, offered a more measured but no less direct assessment of the situation. When asked if the heat shield would crack again on Artemis II, he confirmed, "Yes, it is going to crack." The critical unknown, he clearly implied, was whether it would crack enough to cause a fatal breach in the vehicle's integrity. Adding further to these mounting concerns, NASA radiation expert Steve Scotty from the Langley Research Center highlighted another deeply uncomfortable reality about the heat shield. The AVCoat material itself actually changes its physical properties approximately every 20 seconds during the intense heat of atmospheric reentry. The current computer models, he suggested, simply cannot fully capture the complex behavior of a substance that is actively transforming in real time, all while being simultaneously heated to 5,000 degrees and battered by immense aerodynamic forces. Compounding this uncertainty, the SLS program manager, John Honeycutt, provided an official estimate that the mission carried somewhere between a 1 in 1, 2 and a 1 in 5, 0 chance of failure. Such an extraordinarily wide range in risk assessment does not reflect confidence. On the contrary, it reflects a state of fundamental uncertainty about the true nature of the risks involved. And yet, despite these profound and publicly aired questions, the official Flight Readiness Review on March 12, 2026, produced a unanimous go vote from all stakeholders. The mission was formally cleared for launch. The 4-person crew was informed of the decision. The massive rocket was subsequently rolled out to the launch pad. On the evening of April 1st, 2026, 4 human beings climbed aboard their Orion spacecraft. The heat shield positioned just beneath them was the same basic design that had cracked apart during the re-entry of Artemis I. The trajectory was indeed different, and the revised models predicted it would work this time. The engineers who built it insisted it would hold, but the outside experts who understood its failure modes warned that those very models could not be fully trusted to predict reality. The astronauts themselves were fully aware of all of it, the debates, the risks, the dissenting opinions. Months earlier, Mission Commander Reed Wiseman had told reporters that if they precisely adhered to the new re-entry path, the heat shield would be safe to fly. That single conditional word, if, carried the immense weight of 4 human lives and a $9.3 billion national program. The most perilous 5 minutes of the entire Artemis II mission have not yet occurred. They will arrive at the very end of the journey, 10 days from now, when the Orion capsule slams into the upper atmosphere at a blistering 7 miles per second. In that critical moment, the heat shield either holds together or it does not. There is no middle ground. But the structural integrity of the heat shield is only one of the many significant risks that could end this mission in tragedy. To truly grasp the full scope of what these 4 people are facing, we must first understand what happened last night, on April 1st, 2026, when the most powerful rocket ever to carry human beings roared to life from its Florida launch pad. Chapter 2. 8.8 million pounds of force. For weeks, the enormous rocket had stood like a sentinel on the launch pad, It was a gleaming white tower of pure engineering ambition, standing 322 feet tall and weighing 5.75 million pounds, even before being loaded with its volatile fuel. It was bolted securely to Launch Complex 39B at the Kennedy Space Center in Florida, truly hallowed ground in the history of human spaceflight. This was the very same pad that launched Apollo 10 inches 1969, the same pad that sent 3 Skylab missions into orbit, and the same pad that hosted the historic Apollo-Soyuz test project. It was also the departure point for 53 Space Shuttle missions, including the final, fateful flight of the Shuttle Challenger. The 4-person crew arrived at the Kennedy Space Center on March 27th. 9 days earlier, they had entered a strict quarantine back in Houston, a necessary period of isolation from the outside world, designed to ensure that no common cold or stomach virus could ground a multi-billion-dollar mission already delayed for years. By the morning of April 1st, the official countdown was deep into its final tense hours. Down at the launch pad, ground crews had started the delicate and dangerous process of loading propellant. Over 725,000 gallons of supercooled liquid hydrogen and liquid oxygen began to flow into the massive core stage of the Space Launch System. The hydrogen was chilled to an incredible negative 423 degrees Fahrenheit, the oxygen to negative 297. At these extreme cryogenic temperatures, the propellants are dense enough to provide maximum energy, yet they are also volatile enough to turn the 300-foot rocket into an immense explosive device if anything should go wrong during the fueling process. At approximately 2:30 inches the afternoon, Eastern Time, the crew began the process of boarding the Orion spacecraft. They rode a specialized elevator to the very apex of the mobile launch tower, walked across the crew access arm, and stepped into the famous White Room. This is a small, environmentally controlled, enclosed space at the very top of the gantry, a symbolic threshold where astronauts make their final transition from the familiar world below to the complex machine that will carry them away from it. In keeping with a cherished tradition dating back to the Gemini program of the 1960s, each astronaut signed the wall, a signature, a name, a simple, personal mark that says, "I was here. I chose this path." They then climbed into their custom-fitted seats. Reed Wiseman, the commander, Victor Glover, the pilot, and Christina Koch and Jeremy Hansen, the mission specialists. 4 people, occupying 4 seats inside a capsule roughly the size of 2 minivans. There, they were strapped in by technicians, their helmets secured, and then left to wait as the final, critical hours of the countdown ticked by. The countdown, however, was not without its own set of last-minute problems. A sudden issue with the flight termination system briefly put the mission into a no-go state. This critical system is designed to destroy the rocket if it were to stray from its intended flight path after liftoff. Without it, the range safety officer could not ensure the security of the surrounding area. On the ground, engineers scrambled, retrieving legacy equipment from the space shuttle era to validate the system's integrity. As the clock ticked on, the issue was resolved. But the challenges were not over. Soon after, a battery connected to the launch abort system showed an unusual temperature reading. After careful assessment, teams concluded it was merely an instrumentation error, not a genuine hardware failure. With these hurdles cleared, the weather forecast improved, shifting from 80% to 90% favorable. The final poll of the launch team yielded unanimous go calls from every station, and the countdown proceeded into its final tense minutes. At precisely 6:35 inches the evening, Eastern Daylight Time on April 1st, 2026, the 4 RS-25 engines at the base of the core stage roared to life. This was the moment all preparation had led to the birth of a controlled explosion of unimaginable power. These engines share the same celebrated design that powered the space shuttle for 3 decades. Inside their combustion chambers, liquid hydrogen and liquid oxygen mixed under pressures surpassing 3,000 pounds per square inch, generating temperatures that reached nearly 6,000 degrees Fahrenheit. The engines throttled up to full power, and for 7 seconds, flight computers meticulously verified that all four were performing within their designated limits. Only then did the solid rocket boosters ignite. Strapped to either side of the core stage, these twin boosters are the largest solid rocket motors ever constructed for flight, with each one standing 177 feet tall. During the ascent, each booster would burn approximately 6 tons of propellant every second. Combined with the 4 core engines, they generated a staggering 8.8 million pounds of thrust. This figure represents 17% more power than the legendary Saturn V rocket that carried the Apollo astronauts to the moon, making this the most powerful launch vehicle ever to lift human beings into space. With an explosive charge, the hold-down bolts were severed. The mobile launcher released its grip, and 5.75 million pounds of machinery began its ascent from the pad, riding a column of fire that transformed the Florida evening into daylight for miles in every direction. For those watching from a distance, the sound took several seconds to arrive. When it did, it was not an ordinary sound to be heard, but a physical force to be felt. It manifested as a deep, rolling thunder that rattled through chest cavities and shook the very ground beneath their feet. In parking lots miles away, car alarms were triggered by the sheer acoustic energy. The rocket's climb was slow at first, a deliberate and powerful push against gravity. Its thrust-to-weight ratio at liftoff was close to 1.5, meaning for every pound of its mass, the engines produced roughly 1.5 pounds of force. The acceleration was not jarringly dramatic, but rather a steady and relentless build-up of speed. Just 2 minutes after liftoff, the rocket was already 29 miles above the Atlantic Ocean, traveling at 3,100 miles per hour. At this point, the solid rocket boosters had exhausted their propellant. A series of explosive bolts fired, and the two immense, spent casings tumbled away from the core stage, trailing faint wisps of residual flame as they began their long fall toward the ocean below. The core stage engines, however, continued to burn, pushing the spacecraft ever higher. 8 minutes after liftoff, as the rocket reached the very edge of space, the core stage engines cut off. This moment, known as main engine cutoff, was followed by the separation of the core stage, which fell away, leaving the Orion capsule and the interim cryogenic propulsion stage to continue their journey alone above the planet. A single engine burn from this upper stage then pushed them into a stable, low parking orbit. 49 minutes after launch, a perigee raise maneuver refined this path, securing their orbit around Earth. The crew was now in space, but their ascent was far from complete. Just under 2 hours after leaving the pad, the upper stage engine fired once more, this time for approximately 18 minutes. This was the apogee raise burn, a crucial maneuver designed to stretch their orbit dramatically. It pushed the highest point of their trajectory to an altitude of roughly 43,760 miles above Earth. This was a realm of space unseen by human eyes for half a century, nearly 5 times higher than the International Space Station, and the farthest any astronaut had traveled since the Apollo 17 mission in 1972. With the spacecraft now in its vast, elliptical orbit, the mission transitioned from the violence of launch to the quiet, methodical work of living in space. The solar array wings deployed as all 4 panels unfolded from the service module and locked into place. Their photovoltaic cells began drinking in the sunlight, converting it into the electrical power that would sustain Orion for the next 10 days. Inside, astronauts Christina Koch and Jeremy Hansen unstrapped from their seats and commenced the vital task of testing essential life support systems, including the water dispenser, the firefighting masks, and the toilet. It was the toilet, in fact, that would provide its own minor drama. During the checkout procedure, the crew reported a blinking fault light. This small issue prompted a collaborative effort between the crew and mission control in Houston to troubleshoot the system. Eventually, the problem was resolved, and the toilet was restored to normal operations. It was a perfect example of the unglamorous reality of spaceflight, a world where a $300 billion program can be momentarily complicated by a malfunctioning waste management system, a stark contrast to the cinematic version of space exploration. Beyond the technical checklists, the human experience of being in this new environment began to unfold. Commander Wiseman described the powerful ascent as an amazing ride. Pilot Victor Glover, who had hand-flown Orion during a proximity operations demonstration earlier, reported that the spacecraft handled very nicely, calling it very precise. The crew also shared that from their high vantage point, they had already witnessed 2 moonrises, a curious effect of their elongated orbit, carrying them in a long, slow arc around the Earth, causing the moon to grow and shrink in their windows. There was one other moment of tension that went beyond mechanical glitches. For a brief period, NASA lost the ability to hear the crew's responses. While telemetry data from Orion continued to flow normally, confirming the spacecraft itself was healthy, the silence from the astronauts was deeply unnerving. The communications link was soon restored, but the incident was a potent reminder of how unforgiving space can be. Every system and every connection is critical, and when you are farther from home than any human has been in half a century, even a few seconds of silence can make an entire room hold its breath. With the initial orbital operations complete, the crew settled in for a scheduled 4-hour nap. Their wake-up call was set for 7:00 inches the morning Eastern Time on April 2nd, at which point they would begin preparing for the next perigee raise burn. This maneuver was designed to lift the lowest point of their orbit, carefully shaping their trajectory in preparation for what was to come next. Even rest was part of the meticulously planned timeline, a strategic pause before the mission's most pivotal moment. The launch, as successful as it was only the beginning. The rocket had worked, the boosters had separated on cue, the engines had fired on time, and the solar arrays had deployed. Orion was alive and healthy in high Earth orbit with 4 human beings inside. But the hardest part of the mission was not behind them. In less than 24 hours, they would have to make the most critical decision of the entire flight, to fire the engine that commits them to the moon, or to abort and come home. Once that engine fires, there is no turning back, no possibility of a rescue mission, and no quick return. They will be committed to a 250,000-mile journey around the far side of the moon, with nothing but physics and their spacecraft to bring them home. The crew knows this. Mission Control knows this. All the success so far was merely the prelude to a single, irrevocable choice. Tonight, as the world watches, the Orion spacecraft integrity traces its long, looping orbit around the Earth. Inside, 4 people are preparing for the engine burn that will propel them farther from home than any human has ever been. But before we follow them on their voyage to the moon, it is essential to understand not just their mission, but the people themselves. Beyond the press releases and official biographies, we must ask who they are, what they have left behind, and why they chose to board a capsule that some of the most brilliant minds in aerospace believed was not yet ready for a human crew. Chapter 3. The 4 who volunteered. Before every crewed spaceflight, there is a private, poignant moment that cameras rarely capture. It is the instant an astronaut says goodbye to their family, not at the televised press conference, nor during the crew walkout with its waves to the crowd. This happens earlier, in a quiet room, marked by a hug that lingers just a moment too long. It is a moment with a child who cannot quite grasp why their parent must leave, and a spouse who understands the stakes all too well, yet has chosen to support this incredible risk. On the evening of April 1st, 2026, 4 individuals climbed aboard Orion. Each carried with them a lifetime of training and sacrifice, and each of them left someone cherished behind. At the helm of Artemis II is Commander Reed Wiseman, whose journey began in Cockeysville, Maryland. He grew up watching fighter jets streak across the sky, and a formative memory was seeing the space shuttle carried on the back of its Boeing 747 transport plane. That sight solidified his dream to fly. He would go on to join the United States Navy, becoming a pilot who flew the F-14 Tomcat and the FA-18 Super Hornet during combat deployments for Operation Southern Watch, Enduring Freedom, and Iraqi Freedom. A graduate of the U.S. Naval Test Pilot School, one of military aviation's most demanding programs, his experience is vast. In 2014, he spent 165 days aboard the International Space Station as part of Expedition 41, where his crew set a record by completing 82 hours of research in a single week. He later served as NASA's chief astronaut, responsible for managing the entire astronaut corps and assigning crews. When he was named commander of Artemis II, he was already one of the most seasoned figures at the agency, and also a single father to 4 children. The crew's decision to name their spacecraft Integrity was a choice, Wiseman said, reflected their entire approach to training and their core beliefs. When reporters asked him about the vehicle's heat shield, he remained steadfast, stating that investigators had successfully identified the root cause of the earlier issues, which he saw as the most critical step. He voiced his confidence in the newly designed re-entry trajectory. This confidence, however, does not come from a place of ignorance. As a man who has flown combat missions and tested experimental aircraft, he possesses a profound understanding of risk and what the odds truly mean. He knew the dangers, and he climbed aboard anyway. The pilot for the mission is Victor Glover, a captain in the United States Navy. His career is decorated with over 3,500 hours of flight time in aircraft like the FA-18 Hornet, the Super Hornet, and the EA-18G Growler. His logbook includes more than 400 arrested landings on aircraft carriers and 24 combat missions. A graduate of the Air Command and Staff College with multiple advanced degrees, his expertise is unquestionable. In 2020, he piloted the very first operational SpaceX Crew Dragon flight to the International Space Station, where he lived for 168 days, conducted 4 spacewalks, and became the first black astronaut to complete a long-duration mission aboard the ISS. With Artemis II, Glover makes history on a scale that transcends his past achievements. He is the first person of color to ever travel beyond low Earth orbit. Every human who has ever left our planet's immediate vicinity, from the Apollo crews to all who have seen the Earth as a whole, fragile sphere, has been a white American man until now. Glover received this monumental assignment during what he described as a difficult period in his personal life. He shared with reporters the moment he told his family the news, recounting how they simply erupted with joy. His voice cracked as he admitted to the press corps, "I am about to start crying right now. I needed that. I did not even know I needed it." The mission offered him a purpose that rose above the challenges of the moment, and he urged the world to celebrate this milestone in human history. Christina Koch serves as a mission specialist, bringing a remarkable background as an electrical engineer. Long before she ever considered leaving the planet, she actively sought out some of its most remote and harsh environments. She worked at the Amundsen Scott South Pole Station, at research outposts across Antarctica, and at isolated stations for the National Oceanic and Atmospheric Administration. She became an astronaut in 2013, and in 2019, she set the record for the longest single spaceflight by a woman, spending 328 days on the International Space Station. During that time, she also took part in the first all-female spacewalks. As the first woman to journey beyond low Earth orbit, Koch has spoken about its meaning with a blend of humility and striking clarity. She has asked the public to imagine what it feels like to be among those who can call the moon a destination, not merely an object to be admired in the night sky. She expressed her profound hope that Artemis II marks the beginning of an era where every person on Earth can look up at the moon and feel that same sense of possibility. She is a scientist and an engineer, a person who spent years in Earth's loneliest corners, almost as if preparing for a solitude so profound it would make Antarctica feel crowded. For in the moments that Orion passes behind the far side of the moon, its entire mass will sever all communication with Earth, leaving her and her crewmates more alone than any other living human beings. The fourth crew member is Jeremy Hansen, a colonel in the Royal Canadian Air Force, a pilot who flew the CF-18 fighter jet. His love for aviation began at an exceptionally young age. He started flying at 12 with the Royal Canadian Air Cadets, earned his glider wings at 16, and had his private pilot's license by 17. He was hooked on flight before he was even old enough to drive a car. He later became the first Canadian ever to lead a NASA astronaut class, and now the first non-American to fly beyond low Earth orbit. What makes Hansen's journey so extraordinary is that Artemis II is his very first spaceflight. He is a rookie in every sense of the word when it comes to space travel, despite his thousands of hours of experience in some of the world's most demanding aircraft. His maiden voyage will not be a short trip to orbit. It will take him farther from Earth than anyone in history. He is a man from a farm in Ontario, a husband and a father of 3, about to take the most incredible first step imaginable. In training videos, he discussed the mission's practical challenges with his characteristic Canadian understatement. He spoke of managing stowage and trash, and of living for 10 days inside a capsule he compared to a camper van. Yet amidst this modesty, he offered a statement that revealed the mission's profound weight. He described the experience of traveling to the far side of the moon to see Earth from that unique perspective as extraordinary. He said it simply, as if commenting on the weather, but the gravity of his words is immense. It speaks to the spirit of the entire crew. This team is comprised of a test pilot, a combat veteran, a polar scientist, and a fighter pilot who has never before traveled to space. They are 4 individuals who have dedicated years to preparing for a 10-day flight, and who comprehend the inherent risks more deeply than anyone outside of mission control. They were fully briefed on potential heat shield damage, on past institutional disagreements, and on failure odds estimated between 1 in 2 and 1 in 50. Despite this, they chose to proceed. In a symbolic gesture, the crew christened their spacecraft Integrity. The word signifies wholeness and an unbroken state, but it also represents a commitment to moral principles and honesty. For them, the name reflected how they trained, prepared, and ultimately confronted the dangers ahead. In a matter of hours, the trans-lunar injection burn will ignite, an engine firing that will propel Orion from its orbit around Earth and set it on a course for the moon. Once that burn is complete, there is no easy way back, no possibility of rescue, and no quick abort sequence. The 4 astronauts inside will be committed to a 250,000-mile voyage into the most hostile environment humanity has ever faced. But this critical engine burn is merely the start. The journey between our world and the moon is fraught with more peril than many imagine. The very first danger they will encounter is one they cannot perceive, feel, or escape: the invisible ocean of radiation that saturates the space between worlds. Chapter 4. The Point of No Return. On the evening of April 2nd, 2026, approximately 25 hours after leaving the launch pad, the Artemis II crew will arrive at the single most decisive moment of their entire mission. It is not the launch, which is violent but brief, nor is it the lunar flyby, which is breathtaking but passive. Instead, it is a 6-minute engine burn that will determine their fate, whether they continue to the moon or are forced to return home. This crucial maneuver, known as the trans-lunar injection, or TLI, is a demanding and unforgiving exercise in orbital mechanics. The engine on Orion's European-built service module is scheduled to fire for about 6 minutes. Throughout this burn, the spacecraft's speed will climb by approximately 900 miles per hour. While this may not seem like a significant increase, given that Orion is already moving at tens of thousands of miles per hour in its high Earth orbit, those additional 900 miles per hour are everything. They represent the critical difference between endlessly circling our planet and finally breaking free from its gravitational pull. The goal is to reach a precise velocity of 24,500 miles per hour. At this specific speed, Earth's gravity retains just enough influence to ensure the spacecraft is on a free return trajectory. This trajectory is the mission's ultimate safety net. Should a catastrophic failure occur after the TLI burn, if the guidance system goes dark, the main engine refuses to fire again, or another critical system dies, the moon's gravity will act as a failsafe. As Orion swings around the lunar far side, the moon will capture it, bend its path, and sling it directly back toward Earth. No further engine burns would be required. Physics alone would guide them home. This is the very same principle that brought the Apollo 13 crew back safely in 1970. When an oxygen tank exploded on their service module midway to the moon, they could not turn around or use their main engine. But because they were on a free return trajectory, the moon's gravity did the work, swinging their crippled craft around and sending it back to Earth for a successful splashdown. The Artemis II mission was deliberately designed to utilize this exact type of trajectory. This is no coincidence. It is a conscious engineering decision, born from the hard-learned lesson that in spaceflight, things can and do go wrong. When a crisis unfolds 200,000 miles from home, having the laws of physics on your side is the best assurance you can have. But the margin for error is terrifyingly narrow. The free return trajectory works at 24,500 miles per hour, but it fails at 25,000 miles per hour or more. At that higher velocity, the moon would still fling Orion back in Earth's general direction, but the spacecraft would be moving too fast. It would overshoot the planet, flying wide and continuing into the endless expanse of deep space. There would be no rescue, no recovery, and no return, only 4 astronauts drifting silently into the void. That 500 mile per hour difference, a figure that might seem like a rounding error in orbital mechanics, is the line between life and death. The need for precision is absolute. Before committing to the burn, the crew will have spent roughly 24 hours in a high Earth orbit, meticulously testing every one of Orion's systems. This checkout period is their final opportunity to abort the lunar portion of the mission. If a critical failure is detected, a malfunction in life support, a compromise in the navigation system, or a loss of communications, the crew can fire the engine to lower their orbit and be back on Earth within hours. It is the last chance to call it off. A key part of this checkout phase was the proximity operations demonstration. For about 70 minutes, pilot Victor Glover manually flew the spacecraft, executing a series of controlled approaches and retreats relative to the spent upper stage of the rocket. This exercise was designed to test piloting skills that will be vital for future missions, particularly for rendezvous and docking with a lunar lander. Glover later reported that Orion handled beautifully and was very precise. Following the demonstration, Orion performed an automated departure burn, moving it safely away from the discarded upper stage. That stage would later execute its own disposal burn, ensuring it re-entered the atmosphere over a remote stretch of the Pacific Ocean. During this separation sequence, 4 small CubeSats were also deployed from the Orion stage adapter. These miniature satellites, provided by international partners, including Argentina, South Korea, Germany, and Saudi Arabia, are set to conduct their own scientific investigations. The Korean CubeSat carries a material that mimics human tissue, to measure radiation exposure while passing through the Van Allen belts. Others will measure solar X-rays, magnetic fields, and the performance of electrical components in deep space. But these CubeSats, while important, are a sideshow. The main event is the burn, a maneuver governed by the often counterintuitive physics of a journey to the moon. A voyage to the moon is nothing like a terrestrial drive, which has simple phases of acceleration, cruising, and braking. Instead, the journey is more akin to climbing a great, invisible hill, where the slope is the relentless pull of Earth's gravity. The moment the translunar injection burn concludes, and its engine falls silent, the spacecraft begins to slow. For the next 4 days, Orion will constantly decelerate. As with every mile it travels away from Earth, the planet tugs it backward. The change in speed is dramatic. At the end of the burn, Orion is moving at 24,500 miles per hour. By the time it reaches the midpoint between Earth and the Moon, roughly 200,000 miles from home and 41,000 miles from its destination, the spacecraft is crawling through space. Then, something remarkable happens. Lunar gravity takes over. The Moon begins to pull the spacecraft toward itself, and Orion starts accelerating again. It gathers speed as it falls toward the lunar surface, whipping around the far side at close range before its trajectory bends it back toward Earth. This entire flight path traces a delicate figure 8 through space, a cosmic dance between two gravitational masters. Commander Wiseman and his crew have spent years preparing for this pivotal burn, rehearsing it hundreds of times in simulators. They know every procedure, contingency, and abort option by heart. But no simulation can truly replicate the sensation of knowing that in just 6 minutes they will be committed to a journey from which there is no quick return. The final go, no-go decision is a shared responsibility, resting with both mission control in Houston and the crew aboard Orion. If controllers see any concerning telemetry, or if the crew reports a problem, the burn will be waved off. But if all systems are green, the trajectory calculations are confirmed, and the weather in the splashdown zone looks acceptable for their return 10 days from now, the call is made. Go for TLI. For 6 minutes, the engine fires, adding 900 miles per hour to Orion's velocity. As the spacecraft surges forward, Earth's grip begins to loosen. The crew can only watch through their windows as their home planet starts to shrink. There is no turning around now. They are committed. The Moon is 4 days away, and their return is more than a week in the future. Between here and there lies a gauntlet of hazards that no human has faced in over 50 years. The crew of Artemis II has just crossed the point of no return, and the first invisible danger is already all around them. Our planet is enveloped by a shield that most people never consider. It is not forged from metal or glass, but from pure magnetism. This magnetic field, which is generated deep within Earth's core, extends for tens of thousands of miles into space, wrapping our world in an invisible cocoon called the magnetosphere. This field is our silent guardian, deflecting the vast majority of high-energy particles that constantly stream through the solar system. Without it, the surface would be sterilized by radiation in a matter of years, and life as we know it would not exist. Every human who has ever lived has spent their entire existence inside this protective bubble. Even astronauts orbiting 400 kilometers high on the International Space Station remain safely tucked inside, shielded from the worst that space has to offer. The crew of Artemis II is about to leave that vital protection behind. In doing so, they will face radiation hazards that no person has directly encountered since the Apollo program concluded in 1972. This journey into the deep space environment presents a series of obstacles, and the very first is a pair of enormous radiation zones known as the Van Allen belts. These two donut-shaped regions of trapped radiation, which encircle our planet within the magnetosphere, were first discovered in 1958 by the physicist James Van Allen, using data relayed from the Explorer 1 satellite. This is the first major hurdle in a much longer and more hazardous journey. The belts consist of two distinct zones. The inner belt extends from roughly 400 to about 6,000 miles above the surface and is composed primarily of high-energy protons. Farther out, the outer belt stretches from approximately 8,400 to 36,000 miles and is dominated by high-energy electrons. Artemis II is scheduled to cross through these belts multiple times during its orbit-raising maneuvers on the way out and again upon its return. Unlike the Apollo astronauts, who passed through the belts quickly to minimize their time in the highest radiation zones, the Artemis II mission profile includes extended time in high Earth orbit for system checkouts. This means the crew will face prolonged exposure to radiation at levels 50 to 100 times higher than what anyone experiences on the surface of the Earth. These radiation belts are not uniform. They have hotspots and areas of weakness. The most notorious of these is the South Atlantic anomaly, a region where Earth's magnetic field dips unusually close to the surface. This depression allows belt radiation to penetrate to much lower altitudes than elsewhere. Even the International Space Station passes through this anomaly, and astronauts aboard have reported seeing strange flashes of light when they close their eyes. These visual phenomena are a direct result of cosmic ray particles passing through their eyeballs and stimulating retinal cells, a stark, physical reminder of the unseen particles constantly streaming through the spacecraft and their bodies. Yet, the Van Allen belts are merely the gateway. Once Orion clears the outer belt and crosses into cislunar space, the crew leaves Earth's magnetic protection entirely behind. They enter a region where three distinct radiation sources converge, exposing them to the full, unmitigated environment of deep space. The first of these threats is known as galactic cosmic rays. These are protons and heavy nuclei, accelerated to near the speed of light by cataclysmic events across the galaxy, like supernova explosions and other violent phenomena. They arrive from every direction, a constant, pervasive rain of high-energy particles. The energy carried by these particles is almost incomprehensible. A single galactic cosmic ray particle can carry more energy than a fast-pitched baseball, all concentrated into a space smaller than an atom. They are so powerful that they pass through spacecraft walls, as if they were not there, continuing on through human tissue. As they travel, they shatter DNA molecules and create cascades of secondary particles inside the body that can cause cellular damage far from the point of initial impact. There is no practical shielding against the highest energy galactic cosmic rays. It would require meters of solid lead, a mass far too great to carry to the moon. This raises a fundamental challenge for all future long-duration spaceflight. The second major source of radiation originates much closer to home, our own star. These are solar energetic particles, a torrent of protons and electrons blasted outward from the sun during violent events like solar flares and coronal mass ejections. While galactic cosmic rays represent a steady, background threat, these solar particle events are far more unpredictable. They can dramatically intensify the radiation environment with very little warning, posing a dynamic and immediate danger to the crew as they venture farther into the void. While galactic cosmic rays represent a steady and predictable presence, solar particle events are entirely different. Their sporadic nature makes their timing impossible to foresee, as a seemingly quiet sun can suddenly unleash a colossal coronal mass ejection in just a matter of hours. When such an event occurs, a torrent of high-energy particles surges across the solar system, traveling at speeds that can reach millions of miles per hour. For any crew caught in deep space during a major event of this nature, their radiation dose could escalate to dangerous levels almost instantaneously. This is not simply a theoretical risk. In August of 1972, during the window between the Apollo 16 and Apollo 17 missions, the Sun produced one of the most intense solar storms recorded in the 20th century. If an Apollo crew had been traveling to the Moon at that specific moment, they would have been exposed to radiation levels sufficient to induce acute radiation sickness, which presents with symptoms like nausea, vomiting, and a severely compromised immune system. The outcome could even have been fatal, depending on the storm's overall intensity and its duration. It is a sobering realization that the Apollo program's safety was, in this particular instance, a matter of pure luck, since the storm erupted during a fortunate gap in the mission schedule. Although the Sun is currently transitioning out of its solar maximum period, it nevertheless remains highly active. Prior to the Artemis II launch, NOAA forecaster Sean Dahl characterized the situation for reporters as a roller coaster ride, admitting that forecasters simply do not know what to anticipate. This ongoing volatility represents a serious consideration. Two significant solar events that occurred during the current cycle were powerful enough that they would have triggered major concerns for any mission traveling through deep space. In response to this threat, NASA has established a robust and vigilant defense system. The agency's Moon to Mars Space Weather Analysis Office maintains a constant 24-hour watch. As radiation expert Mary Aron explained, their primary focus is on real-time space weather analysis, with a specific priority on identifying solar energetic particles and the solar events that have the potential to generate them. This represents a continuous effort to stand guard against one of the most unpredictable threats inherent in space travel. This planetary-scale vigilance extends all the way to the surface of Mars. NASA's Perseverance rover contributes to this vital effort by observing sunspots on the far side of the Sun, which offers an advanced warning of active regions several days before they rotate into Earth's view. This effectively creates an extraordinary early warning system that spans hundreds of millions of miles. A third source of radiation exposure comes from the residual radiation found within the Van Allen belts, which the crew must traverse again on their journey back home. To counter these various threats, the Orion spacecraft is designed to be significantly better shielded than the Apollo command module ever was. Positioned throughout the capsule, radiation sensors provide constant, real-time data via a system known as the Acute Radiation Risks Tool. Furthermore, every astronaut is equipped with a personal dosimeter that meticulously tracks their cumulative exposure, thereby offering a personalized record of their journey. Data gathered from the uncrewed Artemis I flight has already demonstrated the effectiveness of this modern shielding. During that particular mission, mannequins that were outfitted with specialized radiation vests experienced a 40 to 60% reduction in the radiation dose delivered to their vital organs. These vests function based on a simple but highly effective principle: adding protective mass around the torso. This design provides extra shielding for the bone marrow and internal organs, which are known to be among the body's tissues most vulnerable to radiation damage. Under what are considered normal solar conditions, the total expected radiation dose for the Artemis II crew is projected to be comparable to that received from a whole-body CT scan. This dose represents about 5% of an astronaut's career radiation limit, a significant amount, but one that is considered manageable. That is, of course, assuming the Sun does not have other plans. Perhaps the most forward-looking experiment that is being conducted on Artemis II is a project called Avatar. Before the mission, each of the 4 astronauts provided blood samples for this project. From these individual samples, scientists were able to create remarkable devices known as organ-on-a-chip. These are tiny, sophisticated chips containing miniature, living replicas of bone marrow cells derived from each individual crew member. Bone marrow was chosen for this experiment specifically because it is one of the tissues most sensitive to the damaging effects of radiation. These chips will travel along with the crew inside the Orion spacecraft, experiencing the exact same radiation environment as the astronauts themselves. Once the mission has concluded, scientists will meticulously analyze how each individual chip responded to the journey. This analysis will yield the first truly personalized biological data on how human cells react to deep space radiation beyond the protective Van Allen belts, representing a crucial step toward understanding and mitigating this significant risk for all future explorers. As Alexandra Stankovic, who is the founding director of the Center for Space Medicine Research at Massachusetts General Hospital, has stated, radiation is the #1 limitation to how far humanity can ultimately explore within our solar system. She has described it as the showstopper, the single greatest obstacle that could ground our deepest ambitions unless we can learn how to manage it effectively. The Artemis II mission is poised to provide more data on this critical question than any human spaceflight mission has since the Apollo era. And yet, there is a profound irony inherent in this endeavor. The very astronauts who are gathering this vital information are also the ones who are absorbing the radiation that makes the question so incredibly urgent. For the next 8 days, the crew of Artemis II will be living and working completely outside the magnetic shield that protects all other life on Earth. During this time, their bodies will be constantly penetrated by particles that were born in the fiery hearts of distant, dying stars. Against this invisible onslaught, they have little recourse but to place their trust in their spacecraft's shielding, diligently monitor their instruments, and hope that the sun remains calm until they are safely back home. However, radiation is not the only trial that they will face. The 4 people inside Orion must contend not only with invisible threats from the outside, but also with the very tangible challenge of being confined to a space roughly the size of 2 minivans for the better part of 2 weeks. This is a test of endurance, one that requires them to eat, sleep, exercise, and use the bathroom in extremely close quarters, all while maintaining the sharp focus and precision needed to pilot a spacecraft 250,000 miles away from home. The total habitable volume inside the Orion spacecraft measures 330 cubic feet. While this is roughly 60% more spacious than the Apollo command module, which provided 210 cubic feet for its 3 astronauts, the Orion capsule must accommodate a crew of 4. When this space is divided among them, it provides just 82.5 cubic feet for each person. To put that number into perspective, one can imagine a box that is approximately 4 feet long on every side. Now, picture yourself living inside that box for 10 days with 3 other people, all while hurtling through the vacuum of space at thousands of miles per hour. The level of psychological and physical discipline required for such a feat is immense. The capsule was fundamentally engineered for survival, not for luxury. Every single cubic inch of its interior has been designed with a specific purpose in mind. During the mission's powered phases, which include launch and re-entry, the 4 seats dominate the cabin space. Once the spacecraft is safely in orbit, however, the crew can reconfigure the interior in order to create more living space. The seats that belong to Christina Koch and Jeremy Hansen are folded up and stowed away. For Reed Wiseman and Victor Glover, their seatbacks remain in place, but their footpans are removed. This procedure effectively opens up a slightly larger central area for the crew. In the microgravity environment, the crew is not confined to a traditional floor. They can utilize the full 3-dimensional volume of the cabin. Walls can become floors, and the ceiling can easily become a workspace. In this environment, EV. Before the mission began, the crew worked closely with NASA food scientists, selecting their own menus to balance crucial nutrition with personal taste. Onboard Orion, a water dispenser and a food warmer allow them to rehydrate these meals and heat them to a comforting temperature. But the simple act of eating is a skill that must be relearned in microgravity. It's a strange new reality where crumbs float instead of fall, liquids break free into wobbling spheres, and a dropped fork drifts silently across the cabin, perhaps to be found later against an air vent. This transformation of the mundane is a constant reminder of just how different their world has become. In the weightless environment of space, exercise is not a choice but a biological necessity. Without the constant pull of gravity, muscles begin to waste away, and bones lose their density almost immediately. While ISS astronauts dedicate 2 hours daily to counteract these effects, the Artemis II crew follows a more condensed regimen. They use a remarkable flywheel exercise device, smaller than a piece of carry-on luggage, which can simulate the resistance of rowing, squats, and deadlifts up to 400 pounds. Each astronaut performs about 30 minutes of exercise almost every day. Yet, this routine serves a dual purpose. Beyond maintaining the crew's health, NASA is carefully monitoring how the vibrations from 4 exercising humans impact Orion's sensitive steering systems. On a structure as vast as the space station, such vibrations are easily absorbed, but the smaller Orion is a different matter. Engineers must know if a vigorous workout, 200,000 meters from Earth, could disrupt the ship's orientation, and how life support will manage the resulting spikes in carbon dioxide and humidity. Every action, even a daily workout, is a critical data point. Perhaps the most unglamorous, yet most essential, piece of hardware aboard Orion is its toilet. Officially, the Universal Waste Management System. This advanced commode was 3D, printed from titanium, and is 60% smaller than the one on the space shuttles. The system is designed to vent collected urine into space, while solid waste is stored in containers for the return journey to Earth. A small door offers a measure of privacy, a simple luxury the Apollo crews never knew. On those historic missions, astronauts used plastic bags taped to their bodies in full view of their crewmates, a process many called the most unpleasant part of their journey. Should Orion's toilet fail, as it briefly did on the first night before being fixed, backup systems like foldable urinals and manual collection bags are available, though they offer significantly less dignity. As NASA's Melissa McKinley noted, the system represents an evolution in design, built upon lessons from Apollo, the shuttle, and the space station. The years spent perfecting a toilet reveal everything about the gap between the cinematic dream of spaceflight and its complex reality. Communication with Earth is the crew's lifeline, maintained by the Deep Space Network, a vast international array of giant radio antennae. These stations, located in California, Spain, and Australia, are positioned roughly 120 degrees apart around the planet. This global spacing ensures that as the Earth turns, at least one station is always in line of sight with any deep space mission, creating an unbroken link. But alongside this massive infrastructure, the crew has a more personal connection. Onboard Wi-Fi allows them to send and receive messages and even make video calls. They also hold regular private medical conferences with flight surgeons on the ground, confidentially reporting any symptoms or concerns. This combination of global and personal communication reflects the dual nature of their journey. The daily schedule aboard Orion is structured, though with room for flexibility. Each day is assigned specific tasks that blend preparation with discovery. On day 3, for instance, the crew conducts a CPR demonstration, practicing emergency medical skills in an environment where chest compressions require bracing against a surface, as there is no gravity to push against. They also test the communications link with the Deep Space Network, verifying that voice and data are transmitting clearly across the ever-increasing distance. Day 4 is then dedicated to the mission's scientific heart, reviewing the detailed imaging plan for the upcoming lunar flyby. The crew has only about 3 precious hours during their closest approach to the moon, and every minute of that window must be perfectly choreographed. Which cameras to use, from which windows, at which angles, and on which geographic targets. This intricate plan, rehearsed many times on Earth, will be practiced again as they coast toward their destination. Day 5 brings with it a profound sense of the journey's dual realities: immense danger and incredible discovery. The morning is dedicated to emergency suit practice, where the crew rehearses rapidly donning their orange Orion crew survival system spacesuits. In the event of a cabin depressurization or a fire, these suits are their final line of defense, and they must be able to get into them correctly even with shaking hands and pounding hearts. Then, later that same day, Orion crosses an invisible but monumental boundary, the lunar sphere of influence. This is the point in space where the moon's gravitational pull becomes stronger than Earth's. The transition is gradual, not a physical line, but it marks a deep psychological milestone. The moon is no longer a distant target. It is now the dominant force acting on the spacecraft. Orion is, in effect, falling toward it. The mundane rhythms of life, the carefully planned meals, the scheduled sleep, the daily exercise, the medical checks all unfold against a backdrop of profound cosmic isolation. With every passing hour, the crew travels farther from everything humanity has ever known. The time lag in communications grows, stretching conversations with Earth into a slow exchange. In the windows, our planet shrinks into a beautiful, distant jewel. The silence of the void presses in from all sides. Astronaut Jeremy Hansen described the capsule simply as a camper van, and in size, that is accurate. But this is a camper van hurtling through the emptiness between worlds, carrying 4 people farther from help than any humans have ever been. And on day 6, they will arrive at the place that makes it all worthwhile. There is a side of the moon that no one on Earth has ever seen with their own eyes, not from any field, rooftop, or mountaintop. Our moon is tidally locked with Earth, meaning the same hemisphere perpetually faces our planet, leaving its other half forever hidden from our view. We know it is there, of course. We have photographed it from orbit and mapped its craters and plains with satellites. But since the Apollo program concluded more than half a century ago, no human eye has gazed directly upon the lunar far side from close range. On the 6th day of the Artemis II mission, around April 6, 2026, the crew of Orion will change that. As their gradual approach continues, they will become the first people in over 53 years to witness that mysterious, silent landscape for themselves. By the 5th day of their journey, the moon is no longer a distant point of light, but a colossal sphere that now completely fills Orion's forward viewports. As the spacecraft enters the lunar sphere of influence, the moon's immense gravity begins to take hold, accelerating the capsule faster and faster toward the ancient, cratered world. Through the windows, the crew can distinguish individual craters, mountain ridges, and deep valleys, alongside the dark, smooth plains of ancient lava flows known as Maria. It is a view that very few people have ever witnessed firsthand. However, the spacecraft will not enter a lunar orbit, as Artemis II is designed as a flyby mission. Orion is set to execute a single, elegant pass, threading a precise path around the moon. At its closest approach, the capsule will be just 4,100 miles above the surface. To help grasp the scale, Jeff Rattigan, the lead flight director for Artemis II, offered a simple comparison. Holding a basketball at arm's length would approximate how large the moon will appear to the crew, but such numbers can hardly capture the feeling of that moment. During this close pass, the astronauts have a tightly choreographed window of approximately 3 hours to complete their observation objectives, a sequence they have rehearsed countless times. Their tasks range from naked eye observations to detailed photography, video recording, and the identification of specific geological targets below. This unique trajectory grants the crew an extraordinary opportunity. They will be among the first humans to see vast regions of the lunar far side up close. While the Apollo missions orbited the moon, their paths were near the equator, and their passes over the far side often occurred in darkness. Artemis II, however, approaches on a completely different trajectory. This flight path offers the potential for sunlight to illuminate regions that no human has ever observed directly, raising the tantalizing possibility of new perspectives on this hidden hemisphere. During this pass, the crew will also attempt to capture a new Earthrise photograph. This effort is a direct homage to the iconic image first taken by Apollo 8 astronaut William Anders in 1968, which showed our planet rising over the lunar horizon. That single photograph profoundly altered humanity's perception of itself, revealing Earth as a small, fragile sphere suspended alone in the vast blackness of space. From that vantage point, no borders were visible, no nations could be discerned, only a delicate blue atmosphere enveloping a ball of rock and water. It was a powerful portrait of both unity and isolation. And yet, the Earthrise witnessed by the Artemis II crew will be fundamentally different, not because of the view, but because of the viewers. For the first time in history, the eyes gazing back at Earth from the moon's vicinity will belong to a woman, a person of color, and a non-American. Christina Koch, Victor Glover, and Jeremy Hansen will see the same breathtaking sight that 12 white American men witnessed during the Apollo era, but they will bring with them perspectives that their predecessors simply could not. This new image will therefore carry with it a new layer of meaning for all of humanity. Beyond the visual spectacle, however, lies what may be the flyby's most profound moment, an interval of absolute silence. As Orion swings behind the far side of the moon, the entire lunar mass will position itself directly between the spacecraft and Earth. Radio waves are incapable of penetrating over 2,000 miles of solid rock, and so all communication with mission control will abruptly cease. There will be no voice calls, no data transmissions, and no telemetry. For those precious minutes, the 4 astronauts aboard Orion will be utterly and completely cut off from every other human in existence. While loss of signal was a regular part of the Apollo missions, the context was entirely different. Those astronauts orbited the moon multiple times, losing and regaining contact with each pass, making the silence a routine element of their work. It was an expected, recurring part of their orbital rhythm. For Artemis II, this experience is singular. The crew will pass behind the moon, enter the profound quiet, and emerge only once. This silence is not routine. It is absolute, and by any measure, it will mark the loneliest moments any human beings have ever experienced. It is a moment that truly stretches the definition of solitude. Imagine 4 people inside a capsule the size of 2 minivans. Outside their windows lies the ancient, cratered surface of the far side, illuminated by the sun, but forever hidden from Earth. And behind the moon, obscured by its sheer mass, is our entire world, every person they love, every familiar sound, every signal that connects them to home. All of it is blocked, all of it gone. For those minutes, they are entirely alone, with only each other and the silent, vast universe for company. Astronaut Christina Koch reflected on this very idea before the mission, asking people to consider what it truly means to call the moon a destination. It ceases to be something you merely look at in the night sky and becomes a place you travel to, a world you approach, a body you fly past close enough to see individual boulders on its surface. This journey fundamentally transforms our relationship with our nearest celestial neighbor. And then, as they swing around the far side, another historic record will be broken. Artemis II is projected to pass approximately 4,700 miles beyond the moon. At its farthest point from our planet, the crew will be an estimated 252,799 miles from home. This distance surpasses the previous record for the farthest any human has ever traveled, which was set by the crew of Apollo 13 inches, 1,970 at 248,655 miles. The new record will exceed the old one by about 4,144 miles, a gap roughly equivalent to the distance between New York City and London. There is a somber irony attached to that previous record. The crew of Apollo 13 did not achieve their record distance as part of a triumphant exploration. It was a desperate consequence of a near-fatal disaster. Following an oxygen tank explosion that crippled their service module, they were forced to use the moon's gravity to slingshot their damaged craft back home. Their terrifying improvisation became one of the most celebrated survival stories in history, but their record was a byproduct of a mission gone terribly wrong. In stark contrast, the Artemis II record is a deliberate achievement, born of intention and courage. This crew chose to go. They were fully aware of the risks, understood the controversy surrounding the heat shield, sat through every single briefing, and listened to the dissenting voices. And still, they boarded the spacecraft and rode 8.8 million pounds of thrust into the sky, propelled by the powerful conviction that the mission mattered. Once the far side pass is complete, the elegant physics of the free return trajectory takes over. The moon's gravity bends Orion's flight path, slinging the spacecraft back toward Earth and completing the magnificent Figure 8 journey. The crew has now seen what only a handful of humans have ever witnessed. They have traveled farther from home than any living thing with a heartbeat, and now they are finally heading back. But the awe of their lunar encounter soon yields to a mounting tension. Every mile that brings them closer to Earth also brings them closer to the mission's most dangerous trial, the heat shield test. The fate of their entire journey rests on the next 5 minutes, a fiery return through the atmosphere that will determine whether the mission ends in celebration or catastrophe. The most perilous part of their journey is not the launch, nor the radiation of deep space, nor the isolation behind the moon. It is the act of coming home. Yet before we accompany the crew through that perilous final stage, we must step back and address a question that has shadowed the Artemis program since its inception. It is a question of money, of politics, and of whether the most expensive machine in human history was truly worth building, especially when considering the very different rocket that is waiting in the wings. This brings us to Chapter 8, the $93 billion rocket. The Space Launch System was not born from a grand vision. It was born from a cancellation. In 2010, President Barack Obama brought an official end to the Constellation program, NASA's first major effort to send astronauts back to the moon. The initiative had fallen drastically behind its projected schedule and was losing vast sums of money, compounded by the persistent technical difficulties plaguing its Ares rockets. As no clear path forward was apparent, the decision was made to terminate the program. Ending a large-scale NASA initiative, however, is rarely as straightforward as signing a piece of paper. It has direct consequences for the employment of thousands. The engineers, technicians, and contractors working for Constellation throughout numerous states formed a significant workforce, and their representatives in Congress were committed to ensuring those jobs would not be eliminated. In response, Congress passed the NASA Authorization Act of 2010. This legislation was less a forward-thinking plan for exploration and more a practical directive aimed at ensuring continuity. It required the agency to build a new heavy-lift rocket by repurposing existing hardware from the Space Shuttle program. This included the well-proven RS-25 engines, the solid rocket boosters derived from the shuttle, and a core stage designed after the shuttle's external tank. The mandate was explicit: make use of what was on hand, keep the workforce employed, and assemble the rocket in the same facilities, frequently within the same congressional districts and using the same contractors. The principal goal was not achieving engineering efficiency, but securing jobs in key states from propulsion development in Alabama and core stage assembly in Louisiana to launch operations in Florida and booster production in Utah. A nickname soon arose that perfectly described its political origins: the Senate Launch System. The name endured because it was accurate. The SLS was a vehicle defined as much by the map of congressional districts as by the principles of orbital mechanics. The original financial estimates for this new rocket now look like a complete fantasy. Development costs through 2017 were first projected to be around $18 billion, with an estimated cost of approximately $500 million for each launch. The reality has turned out to be profoundly different. By 2025, the total amount spent on the SLS rocket and its Orion spacecraft had climbed beyond $60 billion. Looking forward, the total program cost through the first Artemis missions is projected to near an incredible $93 billion. This elevates the price of a single launch to about $4 billion. The costs have become so extreme that the White House's own 2026 budget proposal called the SLS grossly expensive, noting it was already 140% over its initial budget. In a frank assessment to Congress, NASA Inspector General Paul Martin declared that his office considered the $4.1 billion per launch cost to be simply unsustainable. At the center of this financial debacle is the program's contracting model. Boeing, the primary contractor for the SLS core stage, is working under a cost-plus contract. This arrangement means the company is reimbursed for all its expenses, plus it receives a guaranteed profit margin. Consequently, if costs go up, the taxpayer, not Boeing, absorbs the overruns. This framework provides little motivation for fiscal restraint. For example, between 2013 and 2017, a time marked by major schedule slips and cost overruns in the hundreds of millions of dollars, Boeing was still given nearly its maximum performance bonus, taking home about $234 million out of a possible $262 million in award fees. In his testimony, Inspector General Martin was blunt, pointing to poor contractor performance by Boeing, flawed planning, and inadequate execution, combined with poor project management and insufficient contract oversight by NASA. The system was, for all intents and purposes, built to reward spending over results, and it has worked exactly as intended. Beyond its price tag, the rocket's very design creates a fundamental problem for long-term sustainability. The Space Launch System is completely expendable. After each mission, every one of its major components is thrown away. The solid rocket boosters drop into the ocean, the huge core stage is jettisoned to be destroyed in the atmosphere, and the upper stage is abandoned in space. Nothing is saved or reused. This dictates that for every single flight, a new rocket must be built from scratch. While this single-use model was the only feasible option for most of spaceflight history, a new paradigm is now available. In 2026, a formidable alternative exists. SpaceX's Starship, at 397 feet tall and generating 17 million pounds of thrust, has nearly double the power of the SLS. Critically, it was designed from day one for full and rapid reusability. Both its super heavy booster and the Starship upper stage are meant to land, be refurbished, and fly again. Elon Musk has speculated that future launch costs might eventually fall below $10 million. Even if the actual price is 10 times that amount, it would still be a tiny fraction of a single SLS mission. This disparity in capability and cost makes for an awkward comparison for the defenders of the SLS program. The contrasting philosophies are perfectly captured by their respective government contracts. For the Artemis program, SpaceX was given a $2.9 billion fixed-price contract for the development of its human landing system. Under this type of contract, SpaceX owns the resulting hardware, and NASA is effectively buying a service. If the company's development costs run high, SpaceX itself must cover the loss. This completely reverses the incentive structure of the SLS. While Boeing is rewarded for spending more money, SpaceX is rewarded for being efficient and successful. In December of 2025, a major leadership change signaled a possible shift in NASA's course. Jared Isaacman, a billionaire entrepreneur who had flown to space on 2 separate SpaceX missions, was confirmed as the new NASA administrator. His resume included the Polaris Dawn mission, which performed the first ever commercial spacewalk. He arrived with a clear directive to cut costs and accelerate schedules, and he moved quickly. By February of 2026, Isaacman had terminated the development of the upgraded Block 1B and Block 2 versions of the SLS, as well as the Advanced Exploration Upper Stage, which saved billions in future spending. The next month, he cancelled the Lunar Gateway, a planned space station in lunar orbit that had already used up over $3 billion, labeling it an unneeded stop. In its place, Isaacman put forth a bold new vision, a permanent moon base at the lunar South Pole, with an estimated cost of $20 billion. The focus had pivoted sharply, away from orbital infrastructure and toward a sustained presence on the moon's surface. Today, the Artemis program is at a pivotal moment. The SLS has proven it is capable. Its inaugural launch on April 1st showed that the most powerful rocket ever built to carry humans is operational. The question that remains is not about function, but about finance. Can the nation afford to spend $4 billion each time it sends a crew toward the moon, especially with a fully reusable and potentially much cheaper alternative being built in South Texas? The $93 billion already invested in the program is a sunk cost, but that investment is not without worth. It has produced a functional rocket, a deep space capsule, ground systems, and the immense institutional expertise needed to operate it all. Whether that money is ultimately considered a wise investment or a wasteful diversion will be determined entirely by what comes next. If the Artemis program can successfully create a permanent human outpost on the moon, history may well judge the cost to have been worth it. Should the Artemis program falter under its own immense financial weight, the Space Launch System might one day be remembered as little more than an extravagant monument to government contracting. Yet, the fierce debate over its budget is not the only pressure bearing down on the mission. A different, more powerful force is now at work, one that has nothing to do with congressional districts or contractor fees. This new pressure is the undeniable force of competition, because America is no longer the only nation in a race to the moon, and its primary contender has a formidable track record of hitting its deadlines. With this, a new chapter in space exploration has truly begun. The original space race was a contest of prestige between two global superpowers. The United States and the Soviet Union poured billions into their programs to prove which system, capitalism or communism, could conquer the heavens first. The Soviets seized an early and commanding lead, launching the first satellite, Sputnik, in 1957. They proceeded to put the first human in space, Yuri Gagarin, in 1961, and soon after achieved the first spacewalk and landed the first robotic probe on the moon. For a time, it appeared they were decisively winning. In response, America went all in. President John F. Kennedy declared that the nation would land a man on the moon before the decade was out, and NASA's funding swelled to nearly 4.5% of the entire federal budget. In 1969, Neil Armstrong's foot touched the lunar surface. America had won the race. And then, just as quickly, America quit. After the final Apollo 17 mission in 1972, no human being would venture beyond low Earth orbit for over 50 years. The great space race was over, it seemed, primarily because there was no one left to race against. Today, however, that situation has fundamentally changed. China has emerged as the most capable and determined challenger to American dominance in space. Unlike the Soviet Union, which ultimately collapsed under its own systemic dysfunction, China is building its space program with methodical precision, generous funding, and an impressive history of delivering on schedule. The milestones China has achieved are striking. In 2019, its Chang'e 4 probe became the first spacecraft from any nation to execute a soft landing on the far side of the Moon. In 2020, the Chang'e 5 mission successfully returned lunar samples to Earth. Then, in 2024, Chang'e 6 brought back samples from the far side, marking another unprecedented global achievement. To date, no other country has managed such a complex feat, which speaks to a clear and deliberate long-term strategy. The next steps in China's lunar ambition are already well in motion. Chang'e 7, scheduled for 2026, is designed to land at the lunar South Pole to survey for water ice and other critical resources. Following that, Chang'e 8, planned for 2029, will begin scouting for the construction of the International Lunar Research Station. Capping off this ambitious decade, China has publicly pledged to land its astronauts, called taikonauts, on the Moon by 2030. This is a timeline the international aerospace community takes very seriously, because China does not tend to bluff. The country has consistently met or even beaten its stated schedules, having built and staffed its own orbital space station, Tiangong, in record time. Further underscoring its capabilities, in recent years, China has launched more orbital rockets than any other nation, and its space budget has grown steadily, while NASA's has often been constrained by congressional battles. In 2021, this new competition took on a more formal structure when China and Russia announced a joint project, the International Lunar Research Station, or ILRS. This ambitious initiative stands as a direct counterweight to the American-led Artemis program. The ILRS is planned in 3 distinct phases: a reconnaissance stage from 2021 to 2025, a construction phase from 2026 to 2035, and a utilization phase from 2036 onward. Significantly, the partnership has already attracted a growing coalition of nations that represents a clear alternative to the Western alliance, including Pakistan, Egypt, South Africa, Venezuela, Thailand, Senegal, and Turkey. And the list continues to grow. On the American side, the Artemis Accords have been signed by 60 nations, establishing a framework of principles for peaceful lunar exploration. These principles include transparency, interoperability between different systems, and the deconfliction of activities to prevent interference. But the Accords are not without controversy. Critics argue that the safety zones they establish around lunar operations could function as de facto territorial claims, something the foundational 1967 Outer Space Treaty was specifically designed to prevent. Seizing on this point, China has framed the American approach as a form of space enclosure, positioning the ILRS as a more equitable alternative that is better aligned with international law. All of this raises the profound question of how to govern a world that has no government. The strategic prize driving both of these ambitious programs is exactly the same: water ice at the lunar South Pole. In 2018, NASA confirmed the presence of this ice in permanently shadowed craters, some of which have not seen sunlight in billions of years. These frozen deposits could completely transform human spaceflight. Water, of course, means drinking water for astronauts. It also means breathable oxygen, which can be extracted through electrolysis. Most importantly, however, it means rocket fuel. The very same propellants that power the SLS and nearly every other chemical rocket, hydrogen and oxygen, can be manufactured directly from this lunar water ice. A base at the South Pole with access to this resource would instantly become the most strategically valuable piece of real estate in the entire solar system. It would function as a refueling station for deep space missions, a staging point for voyages to Mars, and a manufacturing center for propellant that does not need to be hauled up from Earth's crushing gravity at a cost of thousands of dollars per kilogram. In essence, whoever controls that base and its resources could control the infrastructure of deep space exploration for the next century. This single resource could very well dictate humanity's future beyond Earth. Both the United States and China are targeting the exact same region. Both are planning bases, both intend to mine water ice, and critically, they are operating under incompatible legal frameworks. The Artemis Accords establish safety zones around operations, but China does not recognize those zones. If both nations establish operations in close proximity at the South Pole, the potential for interference, whether accidental or otherwise, is very real. This is not science fiction. It is geopolitics projected onto the lunar surface. The same dynamics that drive territorial disputes on Earth, competing claims, overlapping interests, and mutual suspicion will inevitably follow humanity to the moon. The ultimate question is whether this competition can be managed peacefully, or whether the moon is destined to become another arena for great power conflict. This new moon race, however, is not simply a solo sprint. It is a contest between coalitions. Canada's role in Artemis, for example, extends far beyond astronaut Jeremy Hansen's presence aboard the Orion capsule. The Canadian Space Agency developed Canadarm3, a new generation robotic arm originally intended for the Lunar Gateway. While the Gateway's cancellation by Isaacman has created uncertainty about Canadarm3's future, Canada's commitment to the Artemis partnership remains firm. Likewise, the European Space Agency built Orion's critical service module, which provides power, propulsion, and life support. Japan, South Korea, and multiple other Artemis partners are contributing hardware, science, and expertise. Ultimately, the journey back to the moon is not a solo endeavor, but one defined by these global alliances. While not a perfect analogy, the comparison to the original space race is revealing. In the 1960s, the contest was one of ideological dominance, culminating in symbolic victories like footprints and a flag. Today, in the 2020s, the competition is about establishing permanent infrastructure. The future will be marked by lunar bases, mining operations, and interplanetary supply chains. The stakes are no longer symbolic. They are material, strategic, and intended to be enduring. For the 4 astronauts aboard Orion, however, these grand geopolitical strategies are a world away. Their thoughts are not on congressional budgets, competing legal frameworks, or the landing schedules of other nations. Instead, their focus is intensely practical, centered on the systems they must monitor, the procedures they must flawlessly execute, and the growing reality of their homeward journey. With the moon shrinking behind them and Earth swelling ahead, the most dangerous part of their mission draws closer with every passing hour. On day 7 of the mission, Orion slips out of the moon's gravitational grasp and begins its long fall back to Earth. The spacecraft gradually accelerates as our planet's gravity reasserts its hold, bending the elegant figure-8 trajectory back toward its origin. The outbound journey is complete. The return has begun. Officially, this is the crew's day off, but a day of rest, hundreds of thousands of miles from home, is not a conventional one. The astronauts remain vigilant, overseeing systems, confirming communication links, and reviewing procedures. They are also processing the profound emotional weight of what they have just done, witnessing the lunar far side, traveling farther from Earth than any human in history, and passing through the deep silence where no signal could reach them. Now, the mood inside Orion is shifting. The initial awe is giving way to something else entirely. It is not fear, but a sharpened, focused preparation. They know what awaits them at the end of this coast, and they are all too aware of their heat shield's history. Having been briefed on every detail of the damage from the Artemis I mission, they understand the Avcoat material will likely crack again. The only question that matters is whether the cracks will be deep enough to be fatal. This long coast homeward is far from empty time. It is a critical window for scientific investigation that will inform missions for decades. The crew demonstrates Orion's radiation shielding capabilities and practices manual piloting of the spacecraft, gathering essential performance data. They also serve as research subjects, collecting saliva samples for immune system analysis. Scientists are keen to understand if the conditions of deep space can reactivate dormant viruses. This concern arises from studies on the International Space Station, where astronauts have shown reactivation of herpes family viruses, including those that cause chickenpox and shingles. The combined stress and radiation of spaceflight appear to suppress the immune system, allowing such infections to flare up. The implications of this happening in deep space, where medical evacuation is impossible, are serious. At the same time, the Avatar organ-on-a-chip devices continue to gather data. These tiny chips, holding replicas of each astronaut's bone marrow cells, have been exposed to the same radiation as the crew. They are poised to become among the most valuable biological samples ever returned from deep space, eagerly awaited by researchers at numerous institutions. Far from Orion, a small fleet of companions continues its own silent work, painting a more complete picture of the deep space environment. The international CubeSats, which were deployed earlier in the mission, are conducting their own experiments independently. South Korea's K-RAD Cube is measuring radiation levels using a specialized material designed to mimic human tissue. A Saudi space weather CubeSat is diligently recording solar X-rays and magnetic field data. Meanwhile, Germany's TACKLES experiment is studying how electrical components perform under the strain of the deep space environment. And from Argentina, the ATA satellite is collecting detailed radiation spectrum measurements. Each of these small, independent satellites contributes a vital piece to the complex puzzle of deep space, gathering knowledge upon which the safety of future explorers will depend. On days 8 and 9, the tension inside the capsule builds visibly as the crew's focus narrows to a series of critical maneuvers. They perform several return trajectory correction burns, which are small, precise engine firings that meticulously adjust Orion's path. The splashdown zone is a specific patch of water in the Pacific Ocean off the coast of San Diego, and missing it by even a few miles could seriously complicate the recovery operation. The burns must be exact. The crew also tests compression garments designed to help their bodies cope with the crushing G-forces of reentry. After 10 days in microgravity, the human body begins to adapt. Blood redistributes from the legs toward the head, the heart slightly atrophies, and blood pressure regulation shifts. When the G-forces hit, blood will rush from the brain to the feet, which could cause lightheadedness, tunnel vision, or even loss of consciousness during the most critical phase of the mission. The garments, which work like the G-suits of fighter pilots, squeeze the legs and abdomen to prevent this dangerous blood pooling. Day 9 marks the crew's last full day in space, and it is dedicated to final, exhaustive checks. This is the last dress rehearsal before the final performance. They study re-entry procedures one final time, review all possible abort scenarios, check their suit integrity, and test their communications links. They prepare the cabin for the violence of atmospheric entry, stowing any loose equipment and securing anything that might become a projectile under 5 or 6 Gs of force. Commander Wiseman and Pilot Glover meticulously review the hand controller procedures for re-entry. Although Orion's descent is designed to be automated, the crew must be prepared to take manual control if the computers fail. In that scenario, Glover would have to fly the capsule through the atmosphere by hand, adjusting its angle of attack to manage extreme heating and G-forces while aiming for the splashdown zone. It is a contingency no one wants to execute, but they prepare for it anyway because that preparation is what separates survival from catastrophe. The emotional arc of the mission has now shifted completely. The first half was defined by a sense of profound wonder, the awesome power of the launch, the sight of the lunar far side, the achievement of a new distance record, and the unforgettable vision of Earthrise. But the second half is defined by anticipation. Every hour that passes brings them closer to their fiery reunion with the atmosphere. The awe of where they have been is steadily being replaced by the focused tension of what they must now endure to make it home. With every completed system check, the mission draws closer to the moment where engineering yields to physics, a point of no return where the design will either triumph or fail. For the crew, this is their final night in space, spent floating inside sleeping bags mounted to the capsule walls. Through the windows, the Earth has grown noticeably larger, its blue and white expanse filling more of their view with each passing hour, an impossibly beautiful sight against the black void. When they awaken, it will be the 10th and final day. This is the day the service module will be jettisoned, the day the heat shield must confront the atmosphere, and the day a 5,000-degree plasma sheath will envelop their capsule. It is the day the parachutes will either deploy or stay packed, the day they either return home or are lost forever. After 9 days, a journey of 685,000 miles to the far side of the moon, and survival through deep space radiation, only one task remains, and it is the one most likely to be fatal. They are now less than 10 minutes from striking the atmosphere at 25,000 miles per hour. The inferno waiting outside their window will reach 5,000 degrees Fahrenheit, and the shield holding it at bay is the same design that fractured during the Artemis I mission. Everything this journey has been building toward now hinges on these next few moments. Day 10 begins with a carefully orchestrated separation high above the Pacific Ocean. The Orion crew module detaches from the European-built service module, the very lifeline that has sustained it for the past 10 days. In a precise sequence, explosive bolts fire and mechanical latches release, allowing the two halves of the spacecraft to drift apart. The service module, complete with its solar arrays, engine, and propellant tanks, tumbles away on a trajectory that will lead to its complete destruction upon entering the atmosphere. It was designed to be sacrificed, its purpose now fulfilled. The crew module is now alone, a blunt cone of metal falling toward Earth, its descent quickening under the planet's ever-increasing gravitational pull. It is a profound moment of transition as the vehicle sheds its past to face its final trial. Inside, the 4 astronauts are secured in their seats, each wearing their Orion crew survival system suit. These bright orange pressure garments are their last line of defense should the cabin lose pressure. With their visors down, gloves locked, and harnesses pulled tight, they are fully prepared for what comes next. The capsule's reaction control thrusters fire in short, calculated bursts, carefully orienting the vehicle so its heat shield faces forward into the direction of travel. This critical maneuver positions the blunt end, the ablative barrier, as the vanguard between the crew and the atmosphere. This is the moment the entire mission has been designed around. The very heat shield that showed signs of cracking on Artemis I is about to be tested again. But this time, 4 human lives depend entirely on its performance. Orion hurtles toward the Earth at a velocity of approximately 25,000 miles per hour, which translates to 7 miles per second, or roughly 33 times the speed of sound. This marks the fastest crewed atmospheric reentry ever attempted, surpassing even the velocities of the Apollo capsules returning from the Moon, a direct result of Orion's greater mass and steeper trajectory. At an altitude of about 75 miles above the Pacific, the capsule makes contact with the upper, discernible layers of the atmosphere. Here, the air molecules are incredibly sparse, almost a vacuum. Yet, at 25,000 miles per hour, this near-nothingness becomes a formidable obstacle. The capsule compresses the air ahead of it so violently that the gas molecules cannot escape quickly enough. They accumulate, compress, and ignite, forming a shockwave of superheated plasma that completely engulfs the vehicle. The temperature on the exterior of the capsule climbs relentlessly, 1,000 degrees Fahrenheit, then 2,000, 3,000, and ultimately reaching 5,000 degrees, half the temperature of the sun's surface. This plasma begins to glow, shifting from orange to white, and then to a blinding incandescent fury that transforms the windows into walls of pure light. From the ground, the capsule appears as a fiery streak across the Pacific sky, a man-made meteor plunging toward the ocean below. Inside, however, the temperature remains controlled. The heat shield is performing its critical function, Its avcoat material is charring and ablating, a process that carries thermal energy away from the spacecraft as it burns off. This is precisely how it was designed to work. The material sacrifices itself, layer by layer, ensuring the structure beneath remains cool enough to survive. On the uncrewed Artemis I mission, this same material did not behave as expected. It cracked and ejected in chunks, leaving behind gouges and holes that exposed deeper layers to temperatures they were never meant to withstand. To mitigate this risk for Artemis II, NASA altered the flight path. The new plan called for a direct plunge rather than a skip re-entry, which involves bouncing off the atmosphere before entering a second time. While this direct approach is steeper, more intense, and subjects the crew to higher G-forces, it creates a single, continuous heating profile. This avoids the cycles of heating and cooling and prevents gases from building up inside the avcoat, blocks the very conditions suspected of causing the Artemis I failure. It was a calculated trade-off, prioritizing the shield's integrity over crew comfort. The crew is now experiencing forces of approximately 5 to 6 times the force of gravity. At 5 to 6 Gs, each astronaut feels as if their body weighs 5 to 6 times its normal amount. Their arms become heavy, and their heads are pressed firmly back into their seats. Even breathing requires conscious effort. To counteract this, compression garments around their legs and abdomens squeeze tightly, preventing blood from pooling in their lower bodies and ensuring their brains remain supplied with oxygen. This is the kind of extreme environment that fighter pilots train for, and it is no coincidence that 3 of the 4 people aboard Orion have that specific background. Then, the blackout begins. For approximately 5 minutes, the electrically charged plasma surrounding the capsule completely blocks all radio communications. In mission control, an unnerving silence descends. The telemetry screens freeze, displaying only the last data received before the signal was lost. At their consoles, flight controllers can only sit and wait. There are no commands they can send, no adjustments they can make. The crew is utterly alone, their fate determined solely by physics. For those on the ground, these are the longest 5 minutes of the mission. Every person in that room is aware of the heat shield's history, has seen the photographs from Artemis I, and is now staring at a dark screen, waiting for it to flicker back to life. Inside the capsule, the crew can witness the plasma through their windows, feel the powerful deceleration pressing them into their seats, and hear the deep rumble and roar of atmospheric friction vibrating through the vehicle's structure. The entire capsule is shaking. In this moment, the heat shield is either working perfectly or it is failing, and there is no way for them to know for sure. The truth will only be revealed by the temperature gauges on the interior structure, which will tell the final story of the shield's performance. As Daniel Lever noted before the mission, the question was never whether the heat shield would crack. Some cracking was always expected. The critical uncertainty was whether those cracks would be significant enough to compromise the thermal protection system. The outcome of the entire mission depended on a fine line. The difference between controlled, predictable ablation and a catastrophic failure, between small pieces flaking away and large chunks exposing the vulnerable structure. At NASA's Langley Research Center, Steve Scotty articulated the immense challenge of re-entry. The very material of the heat shield transforms roughly every 20 seconds as it plummets through the atmosphere. This presents a profound modeling problem, as it's difficult to capture a substance that is actively changing in real time. It chars, it releases gas, and it ablates, all while cracking and restructuring at a molecular level. This all occurs under the duress of temperatures that can melt steel and pressures that would pulverize concrete. As the critical seconds tick by, the superheated plasma outside begins to thin, and the brilliant orange glow, visible from the windows, starts to fade. The crushing G-forces gradually subside as the capsule decelerates, having now passed through the most intense phase of heating. With the external temperature dropping and the atmosphere thickening, Drag effectively bleeds away the spacecraft's velocity. Soon, radio contact is re-established, and a voice crackles through to mission control. Telemetry screens flicker back to life, streaming vital data. The capsule is intact. The heat shield has held. The crew is alive, but their journey is not quite over. The final stage of the descent begins at approximately 36,000 feet over the Pacific Ocean, initiating the most complex parachute system ever used on a piloted spacecraft. First, 3 small parachutes deploy, their purpose being to pull away a protective cover from the main chute bay. Then, at 24,000 feet, 3 foot drogue chutes unfurl, stabilizing the capsule's orientation and slowing its descent to around 307 miles per hour. The sequence continues at 9,500 feet, where 3 pilot chutes emerge to pull out the 3 main parachutes, each a massive 116 feet in diameter. These enormous canopies are designed to inflate in stages between 8,000 and 4,000 feet, a carefully choreographed process that reduces the capsule's speed from nearly 300 miles per hour to a gentle 17 miles per hour. Just before impact, 5 airbags inflate around the capsule's top, a crucial system designed to ensure it lands upright no matter its orientation upon hitting the water. And then comes the splashdown. The capsule impacts the Pacific Ocean about 50 miles off the coast of San Diego. The date is April 10th, 2026. 10 days have passed since launch, and 685,000 miles have been traveled since leaving Kennedy Space Center. The most perilous return journey in the history of human spaceflight has concluded. But the mission itself is not yet complete. AUS. Navy recovery team is already on the water, and their first priority is to examine the heat shield. This marks the beginning of the next chapter, recovery. The Orion capsule bobs in the vastness of the Pacific, its once white exterior now scorched and blackened by the fury of reentry. The 5 airbags encircling its upper ring keep it floating upright, ensuring the hatch remains safely above the waterline. Inside, 4 astronauts are alive. For 10 days, they have lived in space, and their bodies have begun to adapt. Their muscles have adjusted to weightlessness, and their cardiovascular systems have recalibrated for a world without gravity's constant pull. But now, gravity has returned with a vengeance. Every movement feels laden with immense effort. Their heads feel strange, as the fluids that had been floating freely for over a week now rush back toward their feet. From their perspective, Earth suddenly feels much heavier than they remember. The recovery operation was set in motion days earlier. A contingent of more than 100 personnel from NASA and its contractors, supported by the United States Navy, deployed from Naval Base San Diego approximately 3 to 4 days before the anticipated splashdown. They established a position at a midway point in the Pacific, moving to the precise splashdown coordinates within 24 hours of the capsule hitting the water. An elite team of Navy divers is the first to enter the ocean, approaching the capsule in rigid inflatable boats. Their initial task is one of careful assessment. They inspect the exterior surfaces, checking for any leaking chemicals, searching for residual hotspots from re-entry, and verifying that the capsule is stable and safe to approach. The environment around the capsule is fraught with potential hazards. The heat shield itself is still incredibly hot. Furthermore, the exterior surfaces may be off-gassing toxic hydrazine residue from the reaction control thrusters. The divers, however, are extensively trained to handle these conditions. Once they deem the capsule safe, a tow line is attached. The spacecraft is then carefully pulled toward a San Antonio-class amphibious transport dock. This large Navy vessel features a well deck that can be flooded with seawater, allowing the capsule to float directly inside. The ship's deck is subsequently pumped dry, leaving the capsule resting securely on a specially designed cradle. Only after the capsule is safely aboard the ship are the astronauts extracted. As the hatch swings open, fresh ocean air rushes in, After 10 days breathing a recycled atmosphere inside a sealed environment, the Pacific breeze must feel like a revelation. The crew is helped out with great care. After an extended period in microgravity, simply standing upright is a disorienting experience. Their sense of balance is compromised, and muscles that have not supported their body weight for over a week begin to protest. The astronauts may even require assistance to walk, and medical teams are standing by to immediately assess their condition. NASA recovery engineer Melissa Seiler once described the mission's guiding philosophy with simple clarity. The work is not finished until the crew is ensured a safe return home. But while medical teams focus on the human element, the engineers have their attention fixed on something else entirely: the heat shield. The bottom of the Orion capsule is the very first thing the recovery team examines in meticulous detail. The questions they seek to answer are critical. How did the avcoat material perform under the direct re-entry profile? Did it crack? How much of the material was lost to ablation? Are the gouges observed similar to those from Artemis I, or do they present a different pattern? And does this pattern align with NASA's models, or does it reveal unexpected and potentially concerning behavior? This data is far from a mere academic exercise. It will directly shape the future of the entire Artemis program. If the direct re-entry profile performed as predicted, with the heat shield cracking in manageable ways while maintaining its thermal integrity, then NASA's calculated risk is validated. The decision to proceed with a crewed flight without a prior unmanned test would be retroactively justified, and the program could move forward with confidence. However, if the heat shield performed worse than expected, or if the damage approaches or even exceeds what was seen on Artemis I despite the altered trajectory, then the program would face a genuine crisis. Every subsequent Artemis mission is built upon the same fundamental heat shield design. Artemis III, planned as a rendezvous and docking test in low Earth orbit, would have to be completely re-evaluated. More significantly, Artemis IV, the mission targeted to be the first crewed lunar landing since Apollo 17, could be delayed by years. The stakes could not be higher. NASA has already announced a new heat shield design for Artemis III, one that incorporates modified block density and improved gas venting to address the issues discovered on Artemis I. But a crucial distinction remains. Artemis III is a low Earth orbit mission, meaning its heat shield will not be subjected to the extreme velocities of a lunar return. The first true test of this redesigned shield at full lunar re-entry speed will therefore not occur until Artemis IV, a mission currently scheduled for 2028. The post-flight inspection of the Artemis II heat shield will be a painstaking process lasting for weeks or even months. The eyes of the entire aerospace industry will be fixed on one critical moment. Figures like Charles Kamada and Daniel Lees, along with every heat shield engineer, will be watching with an intensity few can appreciate. The photographs returned from the Artemis II heat shield are destined to become the most scrutinized images in the long history of thermal protection systems. A great deal depends on the story they tell. Beyond this single component, the Artemis II mission represents a gateway to everything that is planned to follow. Under the leadership of NASA Administrator Jared Isaacman, the program has been aggressively restructured. Artemis III, which was once slated to be the first lunar landing of the new era, has been reimagined. It will now be a mission in near-Earth orbit, designed specifically to test the rendezvous and docking procedures with a lunar lander. This is a profound shift in strategy. While it introduces an additional mission between Artemis II and the eventual landing, providing more invaluable test data, it also comes at the cost of time and budget. Consequently, Artemis IV is now targeted as the first crewed lunar landing since 1972, a historic return made possible by a SpaceX Starship-derived human landing system that will ferry astronauts from lunar orbit down to the surface. The mission architecture for this return is intricate. The Orion capsule will journey to the vicinity of the Moon, where the Starship lander will already be waiting, prepositioned in lunar orbit after a series of complex refueling flights. From there, the crew will transfer from Orion to Starship, descend to the lunar surface for a period of exploration, and then ascend back to Orion for the final voyage home. This is not about fleeting visits. The ultimate goal is sustained human presence, a vision that moves far beyond just flags and footprints. Following this initial landing, the plan is for annual missions to build out this new foothold. The centerpiece of this ambition is a base at the lunar South Pole, a site chosen for its potential resources. The vision includes mining for water ice, manufacturing rocket fuel on site, and even growing food in the lunar regolith. These efforts are all in service of testing the technologies and procedures that will one day carry humanity to Mars. The proposed $20 billion moon base that Isaacman announced stands as the most ambitious construction project ever conceived beyond Earth. This lunar outpost would be the most isolated human settlement in history, a reality that brings with it immense challenges. A resupply mission from Earth would take a minimum of 3 days, and a medical evacuation would be measured in days, not hours. This means the crew will need to achieve a degree of self-sufficiency that no prior space mission has ever demanded. It is a profound responsibility, and every lesson learned on Artemis II feeds directly into this monumental vision. The data gathered on radiation exposure, the performance of the life support systems, the behavior of the heat shield, and the human factors of living in a confined spacecraft for an extended duration are all critically important. In this sense, the crew of Artemis II are more than just astronauts. They are pioneers serving as test subjects. Their bodies and their experiences will provide the very data that determines whether humanity can truly survive and work beyond low Earth orbit for long periods. The mission's splashdown is therefore not an ending, but a new beginning. Once the capsule is recovered and the crew is safe, the heat shield will be examined, and the program will advance into a future that is as thrilling as it is uncertain. Each subsequent mission will be more difficult than the last. The challenges will compound, the risks will grow, and the stakes will become ever higher. Yet, if everything works, if every system performs and every lesson is learned, then at the end of this long road, human beings will stand on the moon again for the first time in over half a century. But before we can fully look forward to that moment, we must look back to the launch pad, to the history that haunts it, and to the ghosts of those who walked this same path. The 4 astronauts of this new era are scheduled to make that walk on April 1st, 2026, from a place of profound significance, Launch Complex 39B. This 344-acre site on the eastern shore of Merritt Island, Florida, is a flat expanse of coastal land, a place of sawgrass and salt water, battered by hurricanes and bleached by the relentless subtropical sun. From a distance, it appears unremarkable, an industrial collection of concrete, steel towers, and service roads, culminating in a raised platform where rockets await their journey to the heavens. But this patch of ground has borne witness to more history than almost any other place on Earth. 60 launches have departed from Pad 39B, each one a chapter in the story of exploration. The very first was Apollo, 10 inches May of 1969. That mission was the final dress rehearsal for the first moon landing. Astronauts Thomas Stafford, John Young, and Eugene Cernan flew their lunar module to within just 9 miles of the lunar surface, testing every system and verifying every procedure. They then returned home, paving the way for Apollo 11 to make its historic landing 2 months later. In this way, Pad 39B was instrumental in making the moon landing possible. The pad's legacy continued with 3 Skylab missions launched in 1973 and 1974, which carried crews to America's first space station. Then, in 1975, the Apollo-Soyuz test project lifted off from here, marking the first international docking mission between American and Soviet spacecraft during the height of the Cold War. And after that came the era of the shuttle. Over 3 decades, 53 space shuttle missions launched from Pad 39B. The iconic orbiters Discovery, Atlantis, Columbia, and Challenger all began journeys from this complex, which shared duties with the adjacent Pad 39A, yet Pad 39B holds a particular somber weight in the memory of the space program. It was from this very pad, on January 28, 1986, that the Space Shuttle Challenger launched for the final time. The morning was cold, unusually so for Florida. Overnight, temperatures at the pad had fallen to 36 degrees Fahrenheit, far below the qualified range for the O-ring seals on the solid rocket boosters. The night before, engineers at Morton Thiokol, the company that built the boosters, had voiced grave concerns. They warned that in such cold, the O-rings might fail to seal properly. Their professional recommendation was clear: delay the launch until temperatures rose. NASA management, however, pushed back. The mission had already faced multiple delays, and the agency was under immense pressure to maintain its ambitious launch schedule. The engineers' concerns were discussed, but ultimately they were overruled. The decision was made to proceed with the launch. Just 73 seconds after liftoff, the engineers' fears were realized. Hot combustion gases burned through a failed O-ring on the right solid rocket booster. The resulting flame acted like a blowtorch, impinging on the external tank until it ruptured catastrophically. At an altitude of 48,000 feet, the shuttle broke apart in the sky. All 7 crew members perished, including Krista McAuliffe, who would have been the first teacher in space. The nation and the world watched it happen on live television, a moment of collective trauma. The investigation that followed, led by physicist Richard Feynman and former Secretary of State William Rogers, uncovered a deeply troubling pattern that would echo through NASA's history for decades to come. It was a story of engineering concerns being raised only to be dismissed, of schedule pressure overriding a culture of safety, and of a management team convinced that past successes were a guarantee of future safety. The warnings were not just theoretical. They were in the data from previous cold weather launches, which had shown damage to the O-rings. The evidence was there, but it was tragically ignored. Tragically, 17 years later, this same pattern would repeat itself. On February 1st, 2003, the Space Shuttle Columbia disintegrated during re-entry over Texas and Louisiana. Once again, 7 crew members were lost. The cause of this disaster was traced back to a piece of insulation foam that had broken away from the external tank just 81 seconds after liftoff. This piece of foam struck the leading edge of the shuttle's left wing, puncturing the reinforced carbon-carbon panels that formed its thermal protection system. For the remainder of the mission, the damage went unaddressed. Then, during the intense heat of re-entry, superheated plasma entered the wing through that breach. The internal structure failed, and the shuttle was lost. In a haunting echo of the past, engineers had actually noticed the foam strike on mission imagery while Columbia was still in orbit. The question of what could have been done hung heavy in the air. They raised serious concerns, requesting satellite imagery of the shuttle's wing in order to assess what they feared was absolutely critical damage. That specific request was denied by mission management. The official justification was rooted in a particularly grim reality. Even if the damage was confirmed, there was nothing that could be done about it. The shuttle simply possessed no capability for repairing its delicate heat shield while in orbit. And so, the concern was noted, filed away, and ultimately set aside. Just 14 days later, 7 astronauts were dead. The Columbia Accident Investigation Board would later find that the very same institutional dynamics identified after the Challenger disaster had unfortunately resurfaced. These included immense pressure to adhere to the launch schedule and the normalization of deviance, a term describing how known problems are gradually accepted as routine simply because they have not yet caused a catastrophe. The board also pointed to management structures that filtered bad news before it could reach decision makers, and a culture that rewarded optimism while actively penalizing dissent. It is a historical pattern that casts a long and somber shadow. Charles Kamada flew on Discovery's STS-114 mission in 2005, which was the very first shuttle flight to launch after the Columbia tragedy. He was selected for that crew specifically because of his deep expertise in thermal protection systems. In the years that followed, he led the engineering investigation into Columbia's root cause, dedicating his entire career to understanding exactly how institutional dysfunction could prove fatal for astronauts who placed their trust in those systems. And then he watched it happen again. Not the disaster itself, but the ominous pattern that preceded it. The familiar institutional behaviors, the motivated reasoning, and the outright dismissal of dissenting views. When the Artemis I heat shield returned from its uncrewed flight with unexpected damage, Kamada saw the same dynamics at work. Engineering concerns were raised and acknowledged, but they failed to trigger any decisive action. He observed schedule pressure driving decisions that should have been guided purely by data, and saw computational models used to justify conclusions that the models themselves could not reliably support. Dissenting voices were invited to participate, only to be marginalized when their conclusions were deemed inconvenient. The recurrence of this pattern raises a deeply unsettling question about what we have truly learned from the past. In a public post, Kamada expressed his mounting frustration directly. "Wake up, NASA," he wrote, explaining that his own book had already exposed the corruption that took hold after Columbia. Now, he argued, that very same corruption and dysfunction were being exposed during the Artemis program. He issued a stark warning: do not let Artemis II become another Columbia. This was by no means a casual remark. It was a pointed and deliberate comparison. Kamada is not a crank, nor is he a conspiracy theorist. He is a former NASA astronaut with a doctorate in engineering, a man who flew on what was perhaps the most dangerous shuttle mission in history and then spent years studying why Columbia was lost. When a person with such a unique and relevant background draws a parallel between Columbia's institutional failures and the Artemis II heat shield decision, that comparison carries an undeniable and significant weight. NASA, for its part, strongly disputes this characterization. Laurie Glaze, the acting associate administrator for exploration systems development, told reporters at the Flight Readiness Review that the discussions were extremely thorough, open, and transparent. She said the agency talked extensively about its risk posture and the mitigations in place. That review produced a unanimous go vote. But unanimity in a room full of people who have spent years working toward a single launch date is not the same as a genuine consensus among all qualified experts. The people who were saying no were not in that room. They were on the outside, speaking to reporters, posting on social media, and hoping against hope that they were wrong. This leads to the uncomfortable question that haunts Pad 39B. Should Artemis II have flown unmanned first? NASA could have chosen to repeat the Artemis I mission, but this time using the new, more demanding direct re-entry trajectory. This would have allowed them to validate the heat shield fix without risking 4 human lives. The data would have been definitive. The cost, however, would have been another $4 billion and an additional 2-year delay. The agency chose not to. The reasons were complex, born from schedule pressure on a program already years behind, budget pressure on an agency already billions over budget, and political pressure from an administration that wanted a crewed moon mission on its watch. And, to be sure, there was also the genuine engineering judgment of the majority of NASA's workforce, who believed the heat shield would hold. Whether that judgment was correct will be determined by the post-flight inspection. If the heat shield performed well, the decision to fly with a crew will be vindicated. If it did not, That choice will be examined under the harshest light imaginable, and the ghosts of Challenger and Columbia will be invoked once again. Pad 39B does not forget its dead. The ground itself seems to remember every vibration, the steel tower every flame. The people who work there carry the weight of knowing that this very pad has been the stage for both the greatest triumphs and the greatest tragedies in the history of American spaceflight. The past is always present here. The crew of Artemis II walked the same walkway that the Challenger crew walked nearly 4 decades ago. They rode the same elevator, they entered the same white room, they signed the same wall, and then they climbed into a spacecraft with a heat shield that some of the smartest people in aerospace had argued should not yet carry a crew. The question is whether their courage and the prevailing engineering judgment will be proven right, or whether the pattern of history will repeat itself one more time. There is one question left, the deepest one, which sits beneath all the engineering, politics, and history. Why do we keep doing this? Why do we keep sending people out into the void? This brings us to Chapter 14, Why We Go. Between December of 1972 and April of 2026, no human being left low Earth orbit. For 53 years, an entire generation was born, grew up, grew old, and in some cases died, all without anyone from our species traveling to the moon. The International Space Station was an extraordinary achievement, representing 20 years of continuous human presence in space. But the station orbits at just 250 miles. The moon is 250,000 miles away. This difference is not merely incremental, it is civilizational. Every single member of the Artemis II crew, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, was born after the final Apollo 17 mission. None of them had ever been to deep space. Crucially, none of their trainers had been to the moon either. The knowledge of how to send human beings beyond low Earth orbit and bring them home had to be rebuilt from institutional memory, from archived documents, from retirement interviews with Apollo-era engineers, and from new engineering developed from scratch. It is a sobering thought, an entire body of operational knowledge, the kind that only comes from doing something, not just studying it, was allowed to atrophy for half a century. We knew how to go to the moon in 1972. By 2026, we had to learn how all over again. The Artemis program, then, is not just a space mission. It is a civilizational memory recovery project. The official justification for returning to the moon is a practical one. NASA frames Artemis as a stepping stone to Mars. The moon is 3 days away. Mars is 7 months. It is on the moon that you can test life support systems and validate radiation shielding, preparing for the far longer and more perilous journey that still lies ahead. Before humanity commits to a destination where rescue is impossible, it is only logical to test our capabilities in a place where it is possible. The moon offers a proving ground where, should a critical failure occur, a crew could return home in just 3 days. On Mars, however, a similar crisis would leave astronauts stranded and alone for the better part of a year. This pragmatic approach frames the moon as an essential dress rehearsal. It is here that we will learn to build habitats and endure the rigors of another world. Here, we will practice mining water ice from craters cloaked in permanent shadow, using electrolysis to produce breathable oxygen, and manufacturing rocket fuel from local resources. Every challenge overcome and every system validated on the lunar surface measurably reduces the immense risks of a future Martian expedition. This is the rational argument sound, persuasive, and yet, somehow, incomplete. But that logic alone fails to capture the spirit that compelled 4 astronauts to board a vehicle with a questioned heat shield, riding 8.8 million pounds of thrust into the heavens. Rationality cannot fully account for such courage. Something more profound is at play. Every Apollo astronaut who gazed upon Earth from the moon spoke of a fundamental change in their perception, a phenomenon they named the overview effect. From that vantage point, our world appears impossibly fragile and singular. It hangs in the infinite dark as a borderless blue marble, protected only by a tissue-thin layer of atmosphere, separating all known life from the void. Michael Collins, who orbited the moon by himself while his crewmates walked below, saw Earth as a tiny, fragile-looking ball. For Edgar Mitchell, the sight triggered what he called an explosion of awareness, a deep, physical understanding that all things are connected, that the lines on our maps are fictions, and that our planet is a single, unified system of which we are all a part. The crew of Artemis II is poised to inherit this very legacy. 4 more human beings will look back at our home from the far side of the moon, and for the first time in history, their eyes will belong to a woman, a person of color, and a citizen of a nation other than the United States. With their unique life experiences, Christina Koch, Victor Glover, and Jeremy Hansen will carry perspectives that the all-white, all-male American crews of the Apollo era could not. What new insights will they discover in that profound view? What will they feel, and what will they teach us about ourselves upon their return? Astronaut Christina Koch offered a glimpse into this new mindset before the mission, urging people to consider what it means when the moon becomes a destination. It ceases to be just a light in the sky or an object of distant observation. Instead, it becomes a place you can go, a tangible location that is part of our world, much like a city on the far side of an ocean, remote and difficult to reach, but undeniably real. This transformation of the moon into a reachable place speaks to a powerful, almost primal impulse within our species that refuses to stop reaching. This drive is not always rational or practical. It is the same force that guided the first people across the land bridge into the Americas and inspired the construction of boats to cross vast oceans when the shore offered safety. It is the same spirit that compelled explorers to climb mountains that did not need climbing, to map rivers that did not need mapping, and to ask questions that did not need to be asked. This inherent curiosity seems to be woven into the very fabric of our being, pushing us ever forward into the unknown. Artemis II was, by design, a test flight. No one landed, no flags were planted, and no rocks were brought home. 4 human beings simply flew to the moon and returned. That is the simple summary, and yet it contains everything. The true significance of the mission lies not in the flight itself, but in what it proves. It proves that after 53 years of silence, humanity still possesses the will and the skill to achieve this feat. It proves that the knowledge can be resurrected, and that complex technologies, like the heat shield with all its controversies, can be managed. It demonstrates that the human body can endure the harsh radiation of deep space, and that a crew can live and work effectively for 10 days inside a capsule the size of 2 minivans, bringing their spacecraft safely home. It proves that we can go back, and going back is the essential first step to going farther. Ultimately, the moon is not the final destination, neither is Mars. The true destination is everywhere we have not yet been. It is every question we have not yet answered, and every horizon we have not yet crossed. The moon is simply the next step in our journey, the crucial proving ground for a species that has spent its entire existence on one small planet. Now, we are tentatively, clumsily, and bravely reaching for the next one. The journey is fraught with earthly complications, and we must acknowledge them. The $93 billion price tag is real, as are the heat shield controversy, the institutional dysfunctions, and the political gamesmanship. The cost-plus contracts, the congressional pork, the schedule delays, and the budget overruns, all of these are real. And yet, none of these issues can diminish the fundamental truth of what unfolded on April 1st, 2026. 4 people chose to go. They understood the risks, had studied the odds, and had read the dissenting reports and safety analyses that drew comparisons to the Challenger and Columbia disasters. They looked at all of it, and they walked to the launch pad anyway. They signed the wall of the White Room, strapped themselves into their seats, and felt the force of 8. 8 million pounds of thrust pushed them away from the Earth and toward the sky. They saw the far side of the Moon, broke the human distance record from Earth, and looked back at our world from 250,000 miles away. In doing so, they witnessed what only a handful of people have ever seen. A planet so beautiful and so fragile that the sight of it changes you forever. Before the mission, Reed Wiseman captured this monumental undertaking with simple, powerful words. He said, "The 4 of us, we are ready to go. The team is ready to go. The vehicle is ready to go." Ready to go. 3 words that carry the weight of 53 years of waiting. 3 words that embody the ambitions of a species that cannot stop exploring. 3 words that encompass the risk, the wonder, the terror, and the profound beauty of leaving everything you know behind to venture into the dark. Artemis II is not the end of the story. It is the first sentence of a new chapter, one that will include lunar bases, missions to Mars, technologies we have not yet invented, and discoveries we cannot yet imagine. It is a chapter that will be written by people who are alive today, people who watched this launch, who felt the ground shake as a 322-foot rocket was pushed off the pad and into the Florida sky. The Moon is 250,000 miles away. It has been there for 4.5 billion years, and it will remain for billions more, a patient and silent witness in our sky. And now, for the first time in half a century, we are going back. As our deep journey through the Artemis II mission concludes, we reflect on the science of deep space travel and the story of the 4 people brave enough to make the voyage. Your support for calm space is what makes these detailed explorations possible. This great endeavor prompts us to consider a profound question, which we invite you to share in the comments. Would you go? Knowing all that the Artemis II crew knows, from the statistical odds to the history of a cracked heat shield, would you still choose to climb aboard? And what do you believe we will find when we finally land on the Moon again? These are not hypotheticals reserved for astronauts alone. They are questions that belong to all of us. For while the Moon remains a constant, humanity is on the move. Thank you for watching. We will see you in the next investigation.